For centuries, we've wondered about the limits of our universe. Now, armed with advanced technology and revolutionary theories, scientists are venturing beyond the observable cosmos. Join us today as we explore the cutting-edge ideas that are reshaping our understanding of reality. From cosmic inflation to multiverse theories, we'll investigate what might exist beyond the boundaries of our known universe. The current scientific understanding suggests that the universe is vast beyond our wildest imaginations, spanning approximately 93 billion light-years in diameter. This immense expanse contains an estimated 2 trillion galaxies, each filled with countless stars and planets. The sheer size of the universe challenges our understanding of scale and distance, stretching the limits of human comprehension. As for its shape, the universe appears to be flat when viewed on a large enough scale. This conclusion stems from measurements of the cosmic microwave background radiation, which is the afterglow of the Big Bang. Despite its flatness, the universe is not simply two-dimensional. Instead, it is three-dimensional space that curves, and different models of the universe propose various geometries depending on its overall density and expansion rate. The concept of curvature leads to intriguing possibilities. If the universe is underdensed, it could eventually expand forever, creating an open and hyperbolic structure. On the other hand, if it is overdensed, it might collapse back on itself, resulting in a closed spherical shape. Currently, evidence leans towards a critical density, leading us to understand the universe as mostly flat with localized curvatures, influenced by the presence of galaxies and dark matter. There is also the possibility that the universe is infinite, extending far beyond the observable portion we can see. Each point in our universe could theoretically be part of a much larger continuum that stretches beyond our observational limits. This notion invites questions about what lies beyond our reach and encourages scientists to explore the nature of existence itself, revealing the remarkable complexities of the cosmos we inhabit. Scientists define the edge of the observable universe based on the distance light has traveled since the beginning of the cosmos, approximately 13.8 billion years ago. This limit marks the point beyond which light has not had enough time to reach us due to the finite speed of light. Thus, the observable universe is the portion we can see, all limited by the age of the universe and the speed at which light travels. The concept of the edge is somewhat misleading, as there isn't a physical boundary or wall marking an end to the universe. Instead, the observable universe is often depicted as a sphere surrounding us, with Earth at its center. The radius of this sphere is about 46 billion light-years, meaning that while the universe may be 13.8 billion years old, the expansion of space has allowed us to see light from regions much farther away than that initial distance. This sphere represents all the objects whose light has had time to reach us, but there are parts of the universe beyond that edge that we will never be able to observe. Due to the ongoing expansion of the universe, regions beyond the observable limit are moving away from us faster than light can travel, making it impossible for their light to reach us, even over infinite time. As a result, scientists understand that while we study the universe based on what we see, much remains hidden from our view. Understanding this edge also poses intriguing questions about the universe's overall structure. The regions beyond the observable universe might contain galaxies, clusters, and phenomena similar to what we can see. However, without direct observation, these areas remain speculative, inviting scientific inquiry and exploration into the unknown frontiers of existence. The cosmic microwave background radiation is a faint glow that fills the universe and serves as a remnant of the Big Bang. This radiation is essentially the leftover thermal energy from the hot, dense state of the universe, which existed approximately 380,000 years after the initial explosion. At this time, the universe cooled enough for protons and electrons to combine and form neutral hydrogen atoms, allowing photons to travel freely through space. This release of light marks a significant moment known as recombination. As the universe has expanded over billions of years, this ancient radiation has stretched and cooled, shifting into the microwave range of the electromagnetic spectrum. Today, it is detected uniformly across the sky and creates a backdrop of nearly uniform energy temperature, around 2.7 degrees above absolute zero. Detailed measurements of this background radiation have provided crucial insights into the early universe, revealing fluctuations that represent the seeds of structure formation, galaxies, stars, and clusters. The cosmic microwave background also plays a key role in defining the limits of our observable universe. Since it comes from a time when the universe was just beginning to take form, it marks the farthest distance from which we can receive information. The background serves as a sort of cosmic map, illuminating the conditions that prevailed shortly after the Big Bang and providing context for the universe's evolution over time. Investigating these signals allows scientists to make precise measurements of the universe's age, composition, and expansion rate. By studying the small variations in temperature and density of the cosmic microwave background, researchers gain insights into the overall geometry of the universe and the distribution of matter. These insights help to refine our understanding of the observable universe's boundaries and the vast structure extending beyond what we can see. Understanding the universe's boundaries has transformed dramatically over the past century, beginning with the groundbreaking insights of astronomer Edwin Hubble in the early 20th century. Hubble demonstrated that distant galaxies are moving away from us, leading to the discovery that the universe is expanding. This revelation fundamentally changed our perception of the cosmos, suggesting that the universe had a beginning, which became known as the Big Bang theory. As technology advanced, so did our methods of observing the universe. The development of radio telescopes, satellites, and space observatories allowed scientists to peer deeper into space than ever before. The detection of the cosmic microwave background radiation in the mid-20th century provided strong evidence for the Big Bang theory and offered a glimpse into the early state of the universe. These findings led to better estimates of the universe's age and the contents that fill it, such as normal matter, and dark energy. In recent decades, cosmologists have further refined our understanding of the universe's boundaries with the introduction of sophisticated models and simulations. These models incorporate the latest observations from numerous telescopes, including the Hubble Space Telescope, which has contributed significantly to our knowledge of the expansion rate of the universe and the distribution of galaxies within it. Newer satellite missions, such as the Planck mission, have provided detailed measurements of the cosmic microwave background, allowing for more exact calculations of parameters like the density of ordinary matter and the influence of dark energy. Today, our understanding emphasizes that while the observable universe has a defined limit, the universe itself may be vastly larger or even infinite. As our observational techniques continue to improve, so does the potential to answer fundamental questions about the nature of space, time, and the very boundaries of reality itself. The journey of discovery is ongoing, each piece of new information reshaping our comprehension of the cosmos. A variety of sophisticated tools and technologies are employed to study the farthest reaches of our universe, enabling scientists to gather crucial data about celestial phenomena. One of the most significant advancements is the development of powerful telescopes, both ground-based and space-based. For instance, the Hubble Space Telescope has provided breathtaking images and vital information since its launch in 1990. Its location above Earth's atmosphere eliminates atmospheric distortion, allowing clearer observations of distant galaxies, nebulae, and exoplanets. Another groundbreaking tool in cosmology is the use of radio telescopes, which detect cosmic radio waves emitted by celestial objects. Arrays like the Very Large Array in New Mexico and the Square Kilometre Array, which is under construction, enable astronomers to study the universe at wavelengths that can reveal phenomena such as pulsars, cosmic microwave background fluctuations, and the morphology of galaxy clusters. These radio observations complement optical data, creating a more complete picture of the cosmos. Space missions have also played a crucial role in advancing our understanding of the universe's limits. The Planck satellite, launched in 2009, mapped the cosmic microwave background radiation across the entire sky with exceptional precision. This allowed scientists to glean insights about the universe's early conditions and to measure its expansion rate and content distribution. Similarly, missions like the James Webb Space Telescope are designed to explore the infrared spectrum, revealing information about the formation of stars and galaxies that existed shortly after the Big Bang. Computational technologies also form an essential part of modern astrophysics. Advanced simulations and algorithms help researchers model cosmic structures and predict their behavior over time. These computational tools rely on massive datasets gathered from observations, allowing scientists to test theories and refine their understanding of the cosmos's architecture. Together, these technologies equip scientists with the means to probe deeper into the universe, pushing the boundaries of our knowledge further than ever before. Cosmic expansion refers to the phenomenon whereby the universe is continuously growing, with galaxies moving away from each other over time. This concept can be traced back to the observations made by Edwin Hubble in the early 20th century, where he discovered that distant galaxies are redshifted, meaning their light is stretched to longer wavelengths. This redshift is interpreted as a sign that these galaxies are moving away from us, which led to the conclusion that the universe itself is expanding. This expansion is a result of the Big Bang, which marks the beginning of the universe. Initially, all matter and energy were concentrated in a hot, dense state. As the universe expanded, it cooled, leading to the formation of atoms, stars, and galaxies. Understanding this expansion has been crucial not just for defining the structure of the universe, but also for determining its age and future trajectory. The rate of expansion is measured by a value known as the Hubble constant, which quantifies how quickly galaxies are receding from each other relative to their distance from us. Cosmic expansion significantly influences our understanding of the universe's boundaries. While we can observe a limited portion of the universe based on the light that has reached us since the Big Bang, expanding space also means that there are regions we will never be able to observe. Some galaxies are receding from us at speeds faster than light due to the expansion, making it impossible for their light to arrive here, even over infinitely long timescales. This creates a natural limit to our observable universe, often referred to as the cosmic horizon. Furthermore, the expansion has implications for the universe's ultimate fate. Depending on the density and composition of matter and dark energy in the cosmos, the universe could continue to expand forever, eventually leading to a cold, dark era, or it might slow and recollapse in a big crunch. Understanding cosmic expansion is essential, as it shapes not just our current observations, but also our predictions about the future of the universe and the nature of existence itself. Scientists measure the rate of cosmic expansion using a variety of methods, each providing complementary insights into the dynamics of the universe. One of the primary techniques involves observing distant galaxies and their redshift, a phenomenon where the light from these galaxies is stretched to longer wavelengths as they move away from us. By analyzing the degree of redshift, astronomers can determine how fast a galaxy is receding. This measurement is crucial for calculating the Hubble constant, which quantifies the relationship between a galaxy's distance and its recession speed. To obtain accurate distance measurements, astronomers often rely on a class of objects known as standard candles. One prominent example is Type Ia supernovae, which are explosive stellar events that reach a consistent peak brightness. By comparing the observed brightness of these supernovae to their known intrinsic brightness, scientists can determine their distance. Coupling these distance measurements with redshift data helps create a more comprehensive understanding of the expansion rate and the Hubble constant. Another significant method involves measuring the cosmic microwave background radiation. The Planck satellite, for instance, conducted highly precise measurements of this radiation, revealing tiny fluctuations in temperature across the sky. These fluctuations contain information about the early universe and allow scientists to infer its density and overall geometry, providing additional context for the expansion rate. By analyzing the cosmic microwave background, researchers can obtain independent estimates of the Hubble constant. In recent years, tensions have emerged between different measurement techniques, suggesting that the expansion rate may not be as uniform as once thought. While the measurements from the cosmic microwave background and the observations of local galaxies agree to some extent, discrepancies indicate that our understanding of cosmic expansion may be missing key details. This ongoing investigation invites further research, which could lead to groundbreaking insights into the universe's composition and evolution. Through these diverse methods, scientists are continually refining the tools and techniques used to unravel the mysteries of cosmic expansion. Cosmic inflation is a theoretical framework that proposes a dramatic expansion of the universe that occurred just fractions of a second after the Big Bang. This period of rapid expansion, lasting from approximately 10 to the minus 34 seconds to 10 to the minus 32 seconds after the beginning, implies that the universe expanded exponentially in size. During this brief phase, the universe grew from subatomic scales to nearly the size of a galaxy, smoothing out irregularities and homogenizing matter across vast distances. The concept of inflation arose to address certain puzzles that the standard Big Bang model could not explain, such as why the universe appears so uniform on large scales despite containing tiny fluctuations. Inflation posits that the superluminal expansion would stretch any initial irregularities across the universe, leaving a nearly uniform state. This theory also addresses the so-called flatness problem, explaining why the universe appears to have a geometry that is very close to flat. In addition to smoothing out the universe, inflation provides a mechanism for the formation of large-scale structures observed today. The tiny quantum fluctuations present in the inflating universe were stretched to cosmic scales during this rapid expansion and later grew into the clusters of galaxies we see today. These fluctuations have been detected in the cosmic microwave background radiation, providing strong evidence for the inflationary theory. Cosmic inflation has significant implications for our understanding of the early universe. It helps explain the initial conditions necessary for the Big Bang to unfold and suggests that our observable universe could be just a small part of a much larger cosmic landscape. This concept opens up questions about what may exist beyond our observable universe and invites exploration into the fundamental dynamics that govern the cosmos. As research in this area continues, inflation remains a powerful tool for understanding the origins and evolution of our universe. Dark energy plays a critical role in shaping the expansion of the universe, acting as a mysterious force driving its acceleration. Discovered in the late 20th century, dark energy is believed to make up approximately 70% of the total energy content of the universe. Its presence was inferred from observations of distant supernovae that appeared dimmer than expected, indicating that the expansion of the universe is not just happening, but is speeding up over time. One leading hypothesis to explain dark energy posits that it is a constant energy density that fills space uniformly, exerting a repulsive gravitational force as the universe expands. This formulation is often described by the cosmological constant, a term originally introduced by Albert Einstein in his equations of general relativity. According to this theory, as the universe grows, the influence of dark energy becomes more pronounced, countering the effects of gravity that would otherwise slow down the expansion. The acceleration of the universe complicates our understanding of its fate. If dark energy continues to dominate, the universe may expand indefinitely, leading to a scenario known as the Big Freeze. In this outcome, galaxies would drift apart, stars would burn out, and the universe would become a cold, dark landscape devoid of active structures. On the other hand, alternative theories suggest that dark energy could change over time, potentially leading to different scenarios, such as a collapse or a stabilization of expansion. Current research focuses on trying to understand the true nature of dark energy, including whether it is a fundamental property of space itself or a more dynamic field. Observations from ongoing and future projects, including large galaxy surveys and improved measurements of the cosmic microwave background radiation, aim to unravel the mysteries of dark energy and its impact on the evolution of the universe. By studying its effects, scientists hope to gain insights into the ultimate fate of the cosmos and refine their models of cosmic expansion. The Big Rip theory is a hypothesis regarding the ultimate fate of the universe and is closely related to the concept of cosmic expansion. This scenario posits that if the acceleration of the universe driven by dark energy continues to intensify, it could eventually tear apart all structures in the cosmos, from galaxies to atoms. According to this theory, as the universe expands at an ever-increasing rate, the gravitational forces binding galaxies, stars, and even the fundamental forces of nature would be overcome by the repulsive effects of dark energy. In this context, the Big Rip can be understood as a critical point where the fabric of spacetime itself becomes so stretched that everything within it becomes detached. As the expansion accelerates, galaxies would first move away from each other at increasingly greater speeds. Eventually, the gravitational forces holding galaxy clusters together would be undone, followed by the disintegration of solar systems, and ultimately, the destruction of planets and all forms of matter. In the final moments of this scenario, even atomic particles could be torn apart, leading to a universe that is utterly fragmented. The timeline for such an event, under this theory, could span billions of years. Depending on the nature of dark energy, the Big Rip could occur as the density of dark energy increases over time, creating a situation where the expansion rate grows uncontrollably. This leads to the idea that the fate of the universe is intimately tied to the properties of dark energy. If it remains constant or decreases, a Big Rip scenario might not happen, while an increase could bring it into play. The Big Rip theory serves as one of several potential fates of the universe, alongside scenarios like continued expansion leading to a big freeze or a collapse in a big crunch. Current observations and research into the behavior of dark energy are crucial in determining which of these scenarios might be more plausible. As scientists deepen their understanding of cosmic expansion and the nature of dark energy, they continue to explore the implications of these theories for the long-term future of the universe. The concept of a multiverse suggests that our universe may be just one of many distinct universes existing simultaneously. This idea stems from various theoretical frameworks in cosmology and physics, proposing that different universes could have their own unique physical laws, constants, and even dimensions of space and time. The multiverse concept challenges the traditional view of a single, isolated universe, expanding our notions of reality and existence. There are multiple theories that propose the existence of a multiverse. One prominent theory is based on cosmic inflation, which posits that the rapid expansion of the universe shortly after the Big Bang could lead to bubble universes. In this scenario, regions of space inflate at different rates, creating pockets of inflation that each become distinct universes. Each bubble can possess different physical properties, which opens the possibility for universes with varied laws governing their behavior. Another approach to the multiverse idea comes from the field of quantum mechanics. The many worlds interpretation suggests that all possible outcomes of a quantum event actually take place in separate, branching universes. This implies that every choice we make or every quantum decision leads to the creation of a new universe, generating an expansive tapestry of realities that exist parallel to one another. The implications of the multiverse concept are profound. It raises fundamental questions about the nature of existence, reality, and our place within it. If other universes exist with different laws of physics, it brings into question the uniqueness of our universe and suggests that the constants we observe may merely be one set of possibilities among countless variations. This challenges our understanding of cosmology and physics, as well as our philosophical perspectives regarding existence and life. While the multiverse remains a tantalizing hypothesis, it presents significant challenges in terms of empirical verification. Currently, there is no direct evidence for other universes, leading to debates within the scientific community about the multiverse's legitimacy as a scientific theory. As our understanding of cosmology and fundamental physics evolves, the exploration of a multiverse continues to spark curiosity and inspire new lines of inquiry. Several types of multiverse theories have been proposed by scientists, each arising from different foundational principles in cosmology, quantum mechanics, and theoretical physics. One of the most well-known categories is the cosmic inflation multiverse. This theory suggests that during the rapid expansion of the universe, different regions could undergo inflation at varying rates, creating distinct bubble universes. Each bubble could possess its own physical constants and laws. This framework not only explains the uniformity of our own universe, but also allows for an infinite number of other universes with diverse properties. Another prominent theory comes from the realm of quantum mechanics and is known as the many worlds interpretation. This approach posits that every quantum event involving multiple possible outcomes leads to the creation of a branching universe for each possible outcome. In this interpretation, all potential realities coexist in parallel, so that every choice, event, or measurement gives rise to a separate universe, creating an enormous landscape of diverse versions of reality, each reflecting different outcomes of quantum decisions. A third type of multiverse theory is rooted in string theory, particularly through a framework called the landscape multiverse. String theory suggests the existence of multiple dimensions and configurations of matter. As various string theory solutions arise from different compactifications of extra dimensions, each configuration can lead to a distinct universe with its own set of physical laws, constants, and forces. This landscape approach allows for a vast number of potential universes, governed by different fundamental principles. Another intriguing concept involves the ultimate multiverse, where every mathematically possible universe exists. This idea stems from the notion that if mathematical structures exist independently of our universe, then any conceivable universe governed by consistent mathematical laws could also exist. In this view, every possible configuration that adheres to logical principles would manifest as a unique universe. These multiverse theories each present a different perspective on the nature of reality and the cosmos. While they provide fascinating explanations and potential ways to reconcile unanswered questions in physics and cosmology, the lack of direct empirical evidence remains a significant challenge. Ongoing research aims to explore these concepts further, helping to determine their viability and implications for our understanding of the cosmos. The bubble universe theory explains the existence of multiple universes through the concept of cosmic inflation, a period of rapid expansion that occurred just after the Big Bang. According to this theory, the universe underwent an inflationary phase where certain regions of space inflated at different rates. This led to the formation of bubbles, each representing a separate universe that developed independently. In the bubble universe model, inflation occurs throughout the cosmos, but not uniformly. While one region of space might stop inflating, allowing for the formation of galaxies and structures, other regions could continue to expand. Each of these regions can become a self-contained universe with its own unique conditions, constants, and physical laws. Within these bubbles, the processes that govern them can differ dramatically, potentially leading to entirely different fundamental forces than those observed in our universe. This theory helps to address several cosmological questions. For instance, it explains why our universe appears homogeneous and isotropic on large scales, despite containing structures like galaxies and clusters. The rapid inflation would smooth out any irregularities, resulting in a more uniform environment within each bubble once inflation concludes. Additionally, it provides a framework for understanding why the constants of nature in our universe have the particular values they do, as each bubble can have a different set of values arising from the particular dynamics of inflation that ended in that region. Moreover, the bubble universe theory suggests there could be an infinite number of such bubbles, leading to a multiverse where each bubble may harbor life, different types of matter, or even entirely different physical laws. This creates a scenario where realities coexist in a larger cosmic context, fundamentally altering our understanding of existence and the structure of reality itself. Ultimately, the bubble universe theory serves as a compelling model for explaining the diversity of potential universes in a broader framework, enhancing our exploration of the cosmos and inviting further inquiry into the nature of space, time, and existence. The many worlds interpretation of quantum mechanics is a theoretical framework that proposes all possible outcomes of a quantum event actually occur, each in its own separate, branching universe. This interpretation emerged in the mid-20th century, primarily through the work of physicist Hugh Everett III. In conventional quantum mechanics, particles exist in a superposition, simultaneously representing multiple states until an observation is made, resulting in a single outcome. The many worlds interpretation, however, suggests that rather than collapsing to one outcome, every possibility is realized, creating distinct, non-communicating branches of reality. To illustrate, consider a simple quantum experiment where a particle can either spin up or spin down. According to the many worlds interpretation, when the particle is measured, the universe splits into two. In one universe, the particle is found to be spinning up, while in a parallel universe, it is found to be spinning down. This branching process continues for all quantum events, resulting in an infinitely complex web of parallel realities. Therefore, each decision or measurement leads to a new universe, allowing every possible outcome to manifest. This interpretation is closely related to multiverse theories, as it implies the existence of numerous universes that coexist with one another. Each universe in the many worlds framework reflects a different sequence of events, outcomes, and choices. It aligns well with concepts like the bubble universe theory, where each bubble can also act as a separate universe but emerges under different conditions rather than through quantum branching. The many worlds interpretation provides elegant solutions to some of the paradoxes of quantum mechanics, such as the observer effect and wave function collapse. However, it remains a topic of debate among physicists because it challenges our traditional understanding of reality and observation. Critics argue that it lacks direct empirical evidence and raises questions regarding the nature of measurement and reality itself. Overall, the many worlds interpretation enriches the conversation around multiverse theories, suggesting a vast and diverse array of universes stemming from the fundamental principles of quantum mechanics. This connection expands philosophical inquiries regarding existence and the nature of the universe, promoting deeper exploration into the implications of both quantum mechanics and cosmology. String theory and M theory offer a fascinating framework that implies the existence of multiple universes, expanding our understanding of reality beyond the single universe we inhabit. At its core, string theory suggests that the fundamental building blocks of the cosmos are not point-like particles, but rather tiny vibrating strings. These strings can oscillate in different ways, leading to a variety of physical phenomena and particle types we observe. This model inherently supports the idea of a multiverse because the vibrational patterns can correspond to different physical laws and constants. M theory serves as an extension of string theory, proposing that these strings exist in higher dimensions. While string theory typically operates in 10 dimensions, M theory suggests an 11th dimension. This additional dimension allows for even more complex interactions and structures, such as brains, which are multidimensional objects that can harbor entire universes. Each brain can potentially support its own distinct universe with its unique set of physical laws, reinforcing the possibility of a multiverse landscape. The mathematics of string theory and M theory include solutions that describe multiple disconnected universes, often referred to as landscapes. These landscapes arise from the multitude of ways in which strings can compactify or curl up in the extra dimensions, creating an incredible diversity of possible conditions for different universes. Because different energy states can lead to vastly different physical realities, it becomes conceivable that each unique configuration corresponds to a separate universe. Though these theories remain unproven and are still a field of active research, the implications they carry are profound. The landscape of string theory and M theory not only challenges our preconceived notions of existence, but also opens doors to explore how universes might interact or be entirely isolated from each other. This intriguing possibility forces us to reevaluate our understanding of space, time, and the very essence of reality itself. Brain cosmology is a captivating aspect of string theory and M theory that examines the role of brains, which are multidimensional objects, in the structure of the universe. In this context, our familiar universe can be conceptualized as a three-dimensional brain existing within a higher dimensional space. Just as a sheet of paper has two dimensions and can exist within the three-dimensional confines of a room, a brain can exist within additional dimensions that are beyond our current sensory perception. One of the most intriguing implications of brain cosmology is the idea that numerous other brains may exist, each potentially housing its own universe with distinct physical laws. These brains can drift within the larger space defined by the extra dimensions. Therefore, different regions of this higher dimensional realm might contain entirely separate universes, which could have different properties, such as varying constants of nature or alternative forms of matter. Brain collisions offer a particularly exciting explanation for cosmic events like the Big Bang. When two brains come close enough to each other, their interaction can lead to a significant energy release, resulting in a cosmic explosion that creates a new universe. This model posits that the Big Bang was not an isolated event, but rather one of many, suggesting a cyclical process in which brains collide, giving rise to new universes in a cosmic rhythm. Furthermore, the dynamics of brain cosmology allow for the potential of universes branching off from one another. As these brains ebb and flow, they can create various cosmic structures that reflect a diverse tapestry of universes where each one may experience its own unique evolution. This framework reshapes our understanding of existence by extending the possibilities of our reality to include an intricate multiverse, where countless parallel and divergent universes may exist, expanding the horizons of cosmological exploration. The concept of extra dimensions in brain theory significantly enriches the discussion of parallel universes, suggesting that what we perceive as a singular reality may be just a thin slice of a much broader cosmic framework. In brain theory, our universe is imagined as a three-dimensional brain embedded in a higher dimensional space, which might consist of additional spatial dimensions beyond the three we experience daily. These extra dimensions provide a rich backdrop for myriad possibilities, including the existence of multiple parallel universes. The relationship between extra dimensions and parallel universes can be understood through the positioning and behavior of these brains. Each brain can be thought of as hosting its own universe, complete with unique physical laws and particles. If these brains reside within the same higher dimensional space, they can exist in proximity, potentially allowing for interactions. However, they can also be separated by large distances in the additional dimensions, creating the possibility that these brains, and consequently the universes they support, remain completely isolated from one another. Moreover, the dynamics of these extra dimensions allow for various configurations and arrangements of brains. This variability means that different universes could emerge based on the specific properties of each brain and its interactions in the higher dimensional space. For example, a universe may possess a different set of fundamental constants or forces depending on how the brain is shaped or positioned in relation to other brains, leading to divergent realities. The interplay of extra dimensions and brain configurations implies a vast landscape of potential universes, where any slight alteration in the parameters governing a brain can result in an entirely new universe. This framework not only introduces the concept of parallel universes existing side by side, but also invites us to ponder the possible connections and divergences among them, hinting at a rich and complex multiverse waiting to be explored. The ekpyrotic universe model presents an alternative perspective on the origins of the universe, departing from the traditional Big Bang theory. This model posits that our universe emerged from the collision of two three-dimensional brains within a higher dimensional space. In the ekpyrotic framework, the universe undergoes an evolutionary process that involves cyclical events where brains collide, creating energy and leading to the formation of new cosmic structures rather than a singular explosive origin. In contrast to the Big Bang theory, which describes the universe as expanding from an infinitely dense point approximately 13.8 billion years ago, the ekpyrotic model suggests that the universe has existed perpetually in a cyclic fashion. This means that there would be a series of brain collisions, giving rise to multiple Big Bangs over infinite time. Each collision sparks a new era of expansion, followed by subsequent contractions, allowing for a continual cycle of creation and destruction rather than a one-time explosive event. One of the key differences lies in how each model accounts for the uniformity and large-scale structure of the universe. The Big Bang theory relies on an inflational phase to explain observations such as the cosmic microwave background radiation and the homogeneous distribution of galaxies. The ekpyrotic universe, on the other hand, attributes these features to the interactions and dynamics of colliding brains. This interplay allows for a variety of outcomes, maintaining a consistent cosmic background without requiring a rapid inflationary expansion. Furthermore, the ekpyrotic model provides a framework to explore additional dimensions and the nature of space-time continuum in ways that the Big Bang theory does not. By integrating concepts of string theory and higher dimensional spaces, the ekpyrotic approach opens up new avenues for understanding the fundamental fabric of reality, challenging our conception of time and existence itself. Through this lens, the universe is not merely a consequence of a singular event, but part of an ongoing cycle of cosmic transformations. Collisions between brains are a central mechanism in the creation of new universes within the framework of brain cosmology. When two three-dimensional brains approach each other within a higher dimensional space, they can engage in a powerful interaction. This interaction is akin to the collision of two massive objects, where the energy released can be immense, resulting in a cosmic event capable of giving rise to a new universe. During such a collision, the energy concentrated in the brains can trigger a significant event similar to what we understand as the Big Bang. This is where the ekpyrotic model sheds light on the nature of these cosmic births. When the brains collide, they can release a tremendous amount of energy, inflating a region of space and creating the fundamental particles and forces that will define the newly formed universe. This process forms the foundational elements of our cosmos, leading to the expansion and evolution of that universe into its distinct reality. In this scenario, each brain collision produces a discrete universe with its own unique physical laws and properties. The particulars of these laws depend on the characteristics of the brains involved, including their energy levels and the configuration of their interactions in the extra dimensions. Therefore, varying conditions during each collision can result in a rich diversity of universes, each with the potential for different types of matter and fundamental forces. Moreover, this model supports a cyclical view of the universe's existence. As brains continue to move and occasionally collide, the formation of new universes can become a recurring phenomenon, suggesting that what we experience as our universe today may be one of countless others that have emerged from similar interactions over cosmic time. This ongoing cycle propels us away from a singular inception point, painting a picture of a dynamic multiverse, constantly giving birth to new realities through the energetic dance of brains in higher dimensions. Observational evidence for brain cosmology remains largely indirect, as the concepts and characteristics associated with this model are challenging to test with current technologies and methodologies. However, certain features of the universe observed through cosmological studies provide intriguing hints that could support brain cosmology and related theories. One significant area of exploration lies in the cosmic microwave background radiation, which is a remnant of the early universe's hot, dense state. The patterns and fluctuations within this radiation help cosmologists understand the universe's formation and evolution. Although the standard model of cosmology adequately explains these observations through inflationary theory, some researchers argue that the unique signatures resulting from brain interactions, such as the potential effects of brain collisions, could manifest in the cosmic microwave background as well. Characteristics such as variations in temperature or polarization might arise from the unique dynamics introduced by brain interactions. Another aspect pertains to the distribution of large-scale structures in the universe, such as galaxies and galaxy clusters. Brain cosmology suggests that these structures could form differently as a result of brain dynamics and their interactions within higher dimensions. Recent surveys mapping the distribution of matter in the universe may provide insight into whether these features align with predictions made by brane cosmology, indicating a need for deeper analysis and more specific models to be tested against observational data. Gravitational waves also hold potential as a source of evidence for brane cosmology. The collisions between branes might create ripples in space-time that could be detected as gravitational waves. If scientists can discover signatures or patterns within gravitational wave emissions that correlate with brane collision events, it could lend support to the theory. While brane cosmology still needs a solid observational foundation, advancements in technology and cosmological surveys may one day reveal more definitive evidence. The exploration of the universe's fabric continues to challenge scientists and inspire new approaches, underscoring our understanding's evolving nature. As we peer deeper into the cosmos, the subtle signs of brane interactions may eventually come into clearer focus, potentially reshaping our comprehension of the universe itself. Quantum fluctuations are transient changes in energy that occur in very small scales of space and time due to the principles of quantum mechanics. These fluctuations arise from the inherent uncertainty associated with quantum states, where energy levels can spontaneously vary even in what appears to be a vacuum. In simpler terms, quantum fluctuations suggest that empty space is never truly empty. It is filled with virtual particles popping in and out of existence, creating a dynamic and ever-changing quantum landscape. In the context of universe creation, quantum fluctuations play a crucial role, particularly in theories that describe the early universe, such as the inflationary model. During a phase of rapid expansion known as cosmic inflation, the universe grew exponentially in size, and quantum fluctuations that existed in the vacuum could be stretched out. As space expanded, these fluctuations in energy density could lead to varying regions of expansion, sowing the seeds for the large-scale structure of the universe we observe today, such as galaxies and galaxy clusters. Interestingly, some theories suggest that quantum fluctuations might also serve as mechanisms for creating entirely new universes. For instance, in a multiverse scenario, it is posited that a quantum fluctuation could generate a region of space with different properties or constants from our own universe. This new region could be thought of as its universe, fundamentally distinct from others due to the unique energy configurations established during those initial flickers of energy. Essentially, one can envision a plethora of universes emerging, each dictated by the specific qualities of the quantum fluctuations that breathe them into existence. Additionally, the concept of a constantly fluctuating quantum vacuum could align with brane cosmology as well. When branes move in a higher dimensional space, they may interact with the quantum fluctuations in that space, potentially leading to conditions ripe for the creation of new universes or influencing the outcomes of brane collisions. This interplay exemplifies how the principles of quantum mechanics could be deeply intertwined with the dynamics of cosmic creation, suggesting that the universe is far from a static entity and is instead rooted in the fluctuating nature of reality at the quantum level. Vacuum energy is a fascinating concept that arises from the principles of quantum field theory, proposing that even the emptiest regions of space are filled with a residual energy. This energy is a result of quantum fluctuations, where virtual particles continuously pop in and out of existence. When we consider the implications of vacuum energy, it opens up critical avenues for understanding both the very fabric of space within our universe and the potential nature of space beyond it. In a cosmological context, vacuum energy is associated with the phenomenon known as dark energy, which appears to be driving the accelerated expansion of our universe. This energy creates a repulsive gravitational effect, pushing galaxies apart and influencing the overall dynamics of cosmic evolution. As scientists explore the nature of vacuum energy in our universe, questions arise about whether similar energy conditions exist beyond our visible cosmos. If vacuum energy acts as a fundamental characteristic of all spacetime, it may significantly impact the structure and behavior of space outside our universe. The concept of vacuum energy contributes to the understanding of a multiverse scenario as well. In such a framework, different regions of space-time, possibly even entirely separate universes, could emerge as a result of varying vacuum energy conditions. Each of these regions may have different properties, particle types, and fundamental forces based on the unique characteristics of their vacuum energies. This implies that beyond our universe, there may exist an expansive landscape of different universes, each shaped by its vacuum state, leading to a rich diversity of realities. Furthermore, vacuum energy can also relate to the idea of bubble universes, where regions of space undergo phase transitions that result in localized energy fluctuations. Such transitions could give rise to new universes as they inflate dramatically, differentiating them from their surroundings. It suggests compelling dynamics in higher dimensional space, where the properties of vacuum energy may create the conditions necessary for the birth of new cosmic environments. As researchers continue to probe the phenomenon of vacuum energy, our understanding of space and time transcends the limitations of our singular universe. The implications of this energy provide a broader perspective that challenges our understanding of existence itself, suggesting a complex tapestry of interwoven universes underpinned by the unyielding presence of vacuum energy throughout the cosmos. Quantum foam is a concept that arises from the field of quantum mechanics, particularly in the context of quantum gravity. It describes the idea that at extremely small scales, on the order of the Planck length, which is a minuscule fraction of a meter, space-time may be far from smooth and continuous. Instead, it can be thought of as a frothy, ever-changing medium filled with constant fluctuations and energy variations, resembling a turbulent sea of virtual particles and fields. This phenomenon reflects the uncertainty inherent in quantum mechanics, where classical notions of distance and time break down. The implications of quantum foam are profound, particularly when considering the nature of space-time itself. It suggests that the vacuum of space is not merely empty, but rather a vibrant and dynamic entity that could influence the fabric of the universe. These fluctuations might have significant consequences on the larger scale of cosmic structures, potentially affecting how matter organizes and evolves. In terms of universe creation, quantum foam could serve as a potential catalyst for the emergence of new universes. Within this chaotic sea of fluctuating energy, regions could experience intense fluctuations that lead to localized high-energy conditions. If these fluctuations achieve a critical threshold, they could trigger a rapid expansion, resembling a Big Bang-like event, thereby forming a new universe. This idea aligns with certain theories in cosmology, where quantum processes play a decisive role in the genesis of universes. Furthermore, quantum foam may link to the concept of a multiverse. As different regions of quantum foam exhibit diverse energy configurations and fluctuations, each might spawn separate pockets of space-time with distinct physical properties. Consequently, this could create varied universes, each governed by its own unique laws of physics, and enriching the landscape of the multiverse. Exploring quantum foam invites scientists to reconsider the dynamics of cosmic creation and the very nature of reality. By investigating how the unpredictable behavior at the quantum level can cascade into large-scale cosmic phenomena, we gain deeper insights into the origins of the universe and the potential existence of an infinite array of universes shaped by the fundamental building blocks of space-time. Studying quantum fluctuations in the laboratory is a challenging yet fascinating endeavor that involves advanced techniques and precision measurement. Scientists employ various methods to observe these seemingly elusive phenomena, often utilizing high-energy physics experiments, quantum optics, and condensed matter physics to probe the quantum realm. One prominent method involves using laser-based technologies to manipulate and detect quantum states. For example, in experiments with ultra-cold atoms trapped in optical lattices, researchers can create conditions where quantum fluctuations can be observed directly. By cooling atoms to near absolute zero, the particles behave according to quantum mechanics rather than classical physics, revealing fluctuations in their positions and momenta. This setup allows scientists to study how these fluctuations contribute to various quantum phenomena, such as superfluidity and quantum coherence. Another approach involves high-energy particle colliders, such as the Large Hadron Collider. These machines accelerate particles to near light speeds, creating extreme conditions where quantum effects become prominent. By analyzing the outcomes of high-energy collisions, scientists can indirectly observe quantum fluctuations and analyze how they influence the behavior of fundamental particles. This research has led to significant insights, including the confirmation of the existence of the Higgs boson and the exploration of supersymmetry, which are deeply intertwined with quantum field theories. Quantum fluctuations also play a critical role in experiments designed to measure the Casimir effect. This phenomenon arises from the vacuum fluctuations of electromagnetic fields between closely spaced conductive plates, creating an attractive force due to the restriction of these fluctuations. By measuring this force with great precision, scientists gain insights into the nature of vacuum energy, quantum field theory, and the underlying structure of spacetime. The insights gained from studying quantum fluctuations in the laboratory have profound implications. Researchers have deepened their understanding of quantum mechanics, explored the foundations of quantum field theories, and even contributed to developing new technologies, such as quantum computing and quantum cryptography. These experiments not only test the limits of current theories, but also challenge our perceptions of reality, revealing a complex interplay between vacuum fluctuations and the fundamental forces governing the cosmos. As techniques continue to advance, the exploration of quantum fluctuations promises to unveil even more mysteries of the universe, enhancing our understanding of both the micro and macro scales of existence. The zero-point energy field refers to the lowest possible energy state of a quantum system, even when the system is at absolute zero temperature. At this state, particles still possess a residual energy due to the principles of quantum mechanics, where even vacuums are never truly empty. This concept suggests that there is a background energy present in all of space, punctuated by continuous fluctuations of fields and particles that arise spontaneously. Understanding the zero-point energy field has profound implications for both our observable universe and the potential expanse beyond it. One of the key features of the zero-point energy is that it is omnipresent. It permeates space regardless of whether there are particles or matter present. This intrinsic energy field acts as a backdrop to all physical processes and may influence the dynamics of the universe on both small and large scales, providing a rich ground for exploring fundamental phenomena. When considering the implications of the zero-point energy field beyond our observable universe, one enters the realm of speculative cosmology and theories like the multiverse. If the zero-point energy is a fundamental aspect of the fabric of existence, it is conceivable that it could enable the creation of pockets of spacetime in regions beyond what we can currently detect. Different configurations of zero-point energy might lead to the emergence of universes with varying physical properties, governing different fundamental forces or constants. This opens the possibility of a multiverse where each universe could operate under its own unique set of rules, arising from the underlying fluctuations of the zero-point energy. Moreover, the zero-point energy field could also play a role in cosmic inflation. The energy associated with this field may have been critical during the early moments of the universe, driving rapid expansion. If this energy field persists beyond the confines of our observable universe, it may continue to influence the evolution of unobservable regions. These areas could harbor their own distinct universe-like structures, shaped by the same fundamental principles that govern the behavior of our own cosmos. Delving into the nature of the zero-point energy field invites scientists to re-examine notions of reality, time, and space. As they seek to understand its role in the cosmos, profound questions arise regarding the interconnectedness of all things and the potential for an expansive, intricate multiverse sustained by the very energy that reverberates throughout the universe and beyond. Cosmic topology refers to the study of the large-scale structure and shape of the universe, exploring how its geometry and configuration can influence the overall nature of cosmic phenomena. At its core, cosmic topology seeks to understand how the universe is connected and organized, encompassing ideas not only about its curvature, but also about its connectivity in higher dimensional spaces. The shape of the universe is a fundamental question in cosmology, heavily influenced by general relativity and the distribution of matter and energy within it. Traditional views often categorize the universe as either flat, closed, or open, depending on the curvature shaped by gravitational forces. These geometrical properties can substantially affect the universe's history, fate, and the pathways light takes while traveling through it. For example, a flat universe expands forever at a steady rate, while a closed universe may eventually collapse back on itself. However, cosmic topology extends this discussion by considering how the universe might wrap or fold upon itself, creating a more complex structure. It suggests that the universe could have a more intricate shape, like that of a torus or higher dimensional manifolds. This means, visually simplistically, that if you could travel far enough in one direction, you might eventually return to your starting point, similar to how one could traverse the surface of a donut. Understanding cosmic topology can have profound implications for our comprehension of the universe, helping to shed light on questions regarding how we might observe distant galaxies and the cosmic microwave background radiation. According to certain topological models, specific patterns or irregularities could arise based on the shape of the universe, potentially providing observables that scientists could measure and analyze to ascertain the universe's underlying configuration. Researchers utilize sophisticated mathematical models, data from cosmic surveys, and measurements of gravitational waves to probe these topological questions further. Insights gained from these studies could reshape our understanding of cosmic evolution and interactions. Ultimately, cosmic topology not only helps us appreciate the universe's extent, but also inspires inquiries into the fundamental nature and interconnectedness of all things, including the very fabric of space-time itself. The shapes proposed for the universe are intriguing concepts that arise from studies in cosmic topology and geometry. These shapes aim to characterize the large-scale structure of the universe beyond the standard flat, open, or closed models typically explained by general relativity. Some of the more interesting geometric forms include the torus and the Mobius strip, each with unique properties that open new perspectives on the cosmos. A torus, resembling the shape of a donut, is one possible topology for the universe. In this model, space can be connected in such a way that traveling in one direction could lead you back to your starting point after a long journey, giving the impression of a finite universe without boundaries. This configuration suggests that if two observers were to start from the same position facing the same direction, they could eventually meet again, despite the universe appearing infinite on a local scale. The toroidal model offers fascinating implications for the distribution of galaxies and cosmic background radiation, suggesting that certain patterns might recur due to the nature of the space's connectivity. The Mobius strip presents another captivating idea in cosmic topology. It is a surface with only one side and one edge, achieved by giving a strip of material a half twist and then joining the ends together. If the universe were shaped like a Mobius strip, it would encourage unconventional paths through spacetime. An observer traversing this topology could seemingly return to their starting point while experiencing a flip in their perspective of space. This property poses interesting questions regarding the orientation of cosmic structures and the possibility of anomalous phenomena. Other proposed shapes for the universe include the Klein bottle, which is a more complex structure that also possesses non-orientable properties, and higher dimensional analogues like Calabi-Yau manifolds from string theory. Each of these shapes presents unique challenges and opportunities for modeling and understanding cosmic dynamics, influencing how we think about the universe's overall connectivity, history, and evolution. Exploring these varied shapes enables scientists to expand their understanding of the universe beyond the conventional frameworks, potentially revealing insights into its ultimate fate and the underlying principles governing cosmic phenomena. As observational techniques and data analysis improve, researchers continue to investigate these fascinating ideas, hoping to uncover the universe's intricacies and the implications of its shape on our understanding of reality. The topology of the universe significantly influences what might exist beyond our observable boundaries by shaping the connectivity and structure of spacetime itself. Depending on the specific geometric configuration, the implications for unobservable regions can vary tremendously, leading to several intriguing possibilities about the nature of the universe beyond what we can see. If the universe has a compact topology, such as a torus, it allows for the universe to wrap around itself. In such a scenario, this means that distant regions of space could be interconnected in ways that defy our conventional understanding. For example, if you were to travel far enough in one direction, you could eventually return to your original location, as though journeying on a closed surface. This topology could imply that regions just beyond our observable limits may contain replicas or slight variations of what exists within the observable universe, potentially leading to repeated structures or phenomena. In contrast, if the universe takes on a more complex topology, like a Mobius strip or a Klein bottle, the peculiar non-orientable properties of these shapes might suggest an unusual arrangement of space-time without traditional boundaries. This could lead to the existence of regions beyond the observable universe that maintain continuity, yet exhibit diverse physical realities. In this case, traversing certain paths might lead to unexpected transformations in perspective or dimensionality, raising questions about the nature of time, space, and existence outside our observational limits. The implications of cosmic topology extend into the realm of the multiverse as well. If different regions of space-time can possess distinct topological characteristics, it might enable the formation of entirely separate universes, each governed by its own physical laws. In this context, the structure of our universe could exist alongside numerous other universes, potentially leading to a vast and complex multiverse. Observational evidence of such structures could be hinted at by anomalies or patterns in the cosmic microwave background radiation or in the distribution of galaxies. Ultimately, the topology of the universe serves as a lens allowing us to conceive of possibilities beyond our observable boundaries. It encourages us to explore radical ideas about the nature of existence, the interconnectedness of realities, and the very fabric of space-time itself. As research in cosmology progresses, a deeper understanding of cosmic topology could reveal profound insights into the universe's structure and the existence of realms yet to be observed. Observational evidence supporting different cosmic topology theories is still a developing field, but scientists have been employing various methods to assess cosmic structures and their implications. While definitive proof for specific topologies remains elusive, several lines of inquiry provide intriguing hints that could point toward non-trivial cosmic shapes. One of the primary avenues for investigating cosmic topology lies in the analysis of the cosmic microwave background radiation. This faint afterglow of the Big Bang contains valuable information about the early universe and its geometry. By examining the temperature fluctuations and patterns in the cosmic microwave background, researchers can look for anomalies or correlations that might suggest a non-trivial topology. For example, if the universe exhibits a compact topology, like a torus, certain patterns might recur due to the universe's closed nature. Specific analyses, such as searching for matching circles or anomalies in the temperature distribution, could indicate that the universe wraps around itself in a defined way. Another approach involves studying the large-scale structure of galaxies and galaxy clusters. If the universe has a unique topological configuration, researchers might observe unusual distribution patterns of galaxies or peculiarities in the voids between them. By mapping the locations of galaxies across vast distances and analyzing their distributions, scientists can look for signatures that deviate from the typical predictions of a simple, flat, or open universe. If certain structures show repetitive patterns or unexpected alignments, this might hint at a more complex cosmic topology. Additionally, gravitational lensing provides another means to detect potential non-trivial topologies. Lensing occurs when massive objects, such as galaxies or clusters of galaxies, bend light from more distant sources, creating multiple images or distorted views. By analyzing the lensing effects and the arrangement of these images, researchers can look for evidence of unusual spatial configurations that might suggest a complex topology. While no conclusive evidence for specific cosmic topologies has yet emerged, These avenues of research indicate that we are on the cusp of expanding our understanding of the universe's structure. Future advancements in observational techniques, refined computational models, and more extensive data sets may lead to critical discoveries that help clarify the topology of the universe and its implications for cosmic evolution and the existence of realities beyond our observable bounds. The concept of cosmic topology presents a fascinating perspective on the structure of the universe, suggesting that it may not be as simple as a vast, infinite expanse. Non-trivial cosmic topologies imply that the universe could have a more complex shape, potentially resembling a three-dimensional space that is wrapped or connected in unusual ways. One common analogy is a donut shape, where traveling far enough in one direction might eventually lead you back to your starting point. This intriguing idea can lead us to reconsider what lies beyond our observable universe. When we talk about what lies beyond the universe, we often think in terms of infinite space containing galaxies and cosmic phenomena. However, if the universe has a non-trivial topology, we might find that beyond our observable limits, there are not just voids of empty space, but potentially more of the same interconnected cosmic structure. This challenges our traditional ideas about edges or boundaries and invites imaginative scenarios about how space might be connected. For example, there could be regions of the universe that are out of sight, yet still part of a larger underlying structure. Furthermore, non-trivial cosmic topologies could have profound implications for the fundamental nature of reality itself. If our universe is part of a larger topology, it raises questions about whether what we perceive as independent galaxies are simply sections of a larger cosmic tapestry. This interconnectivity could also influence the propagation of light and gravitational waves, possibly allowing us to see traces of distant regions that should otherwise be inaccessible. Measurements taken by large-scale surveys of the cosmos could reveal patterns that suggest a more intricate structure, drumming up curiosity about the universe's global features. Considering these ideas reshapes our exploration of cosmic boundaries and inspires new inquiries into the nature of the universe and existence itself. Understanding how the universe might be connected in unexpected ways opens up new avenues for thinking about cosmology, the origin of cosmic structures, and ultimately, our place within this vast, potentially interconnected cosmos. A white hole is a fascinating theoretical counterpart to a black hole, representing a region of space-time that is the opposite of a black hole. While a black hole draws in everything that comes too close, including light, a white hole hypothetically expels matter and energy. In this model, nothing can enter a white hole, making it a one-way exit from the universe or from another region of space-time. This concept intrigues scientists, as it suggests a potential solution to the question of what happens to matter that falls into a black hole. The relationship between black holes and white holes emerges from the equations of general relativity, which describe how mass influences the fabric of space and time. Some solutions to these equations imply that if black holes can exist, white holes might also theoretically exist, serving as endpoints of a singularity. In this sense, one might envision a continuum of sorts, where matter entering a black hole could eventually re-emerge from a white hole in another part of the universe, or even a different universe entirely. This leads to exciting ideas about the interconnectedness of cosmic structures. Moreover, exploring the concept of white holes raises important questions regarding the nature of entropy and information in the universe. Black holes are known to have a reputation for erasing the information of anything that falls inside them, which presents significant paradoxes in theoretical physics. Some researchers suggest that if matter and energy could re-emerge via a white hole, it might offer insights into how information is conserved in the universe. This relationship becomes even more intriguing when we consider the implications for multiverse theories and the nature of time itself. Although white holes remain purely hypothetical at present, studying them alongside black holes can deepen our understanding of the cosmos. They encourage scientists to explore complex ideas about space-time, the flow of energy, and the fundamental laws governing our universe. Their existence, while not yet proven, continues to inspire a wealth of theoretical exploration and stimulates the imaginations of cosmologists trying to unlock the mysteries of the universe. The idea of white holes as gateways to other universes or regions beyond our cosmos is an exciting concept that arises from theoretical physics and speculative cosmology. If we assume that white holes exist, their nature as objects that expel matter and energy implies that they could represent exits from the gravitational pull of black holes. This leads to the tantalizing prospect that they might connect different parts of the universe or even different universes entirely. The hypothetical mechanism involves the idea of a wormhole, a tunnel-like structure that could link a black hole, where matter is absorbed, to a white hole, where it is expelled. In this framework, matter that enters a black hole could potentially be transported through the wormhole and emerge from a white hole in a separate region or dimension. This suggests a cosmic highway of sorts, allowing for transport across vast stretches of space-time, effectively making it possible to traverse great distances in a short amount of time or even to exit our universe altogether. Some theoretical models propose that if our universe is one of many in a larger multiverse, then white holes could serve as points of access between these separate realms. The universe in which we live could be just one bubble in a vast cosmic ocean. If white holes indeed connect to other universes, they may allow for the exchange of information and matter between these diverse realms. This idea prompts fascinating questions about the nature of existence and reality, pushing the boundaries of our understanding. While these concepts remain speculative, they provoke deeper inquiries into the nature of black holes, space-time, and the fundamental forces that govern the universe. The search for empirical evidence supporting the existence of white holes remains an open challenge in theoretical physics. If discovered, white holes could revolutionize our understanding of the cosmos, reshaping how we perceive the relationship between different parts of the universe or even the connectivity between multiple universes. This exploration into the possible gateways is a testament to humanity's unyielding curiosity and the quest for knowledge in an ever-expanding universe. The existence of white holes is primarily supported by the equations of general relativity and various theoretical models that arise from it. These models explore the consequences of black holes while extrapolating their properties to suggest the possibility of their counterparts. One of the foundational ideas stems from the solutions to Einstein's field equations, which describe how matter influences spacetime. The Schwarzschild solution, for example, delineates the properties of black holes, including an event horizon and singularity. By extending this framework, researchers have proposed that a white hole could emerge as a naturally occurring solution in certain conditions. Another pivotal model supporting the concept of white holes is the Kerr solution. This solution describes rotating black holes and extends to scenarios involving rotating white holes. By considering the angular momentum of these objects, physicists have identified features that could imply the existence of structure and dynamics relevant to white holes. This line of inquiry brings into focus the intricate relationship between black hole physics and the potential behaviors of white holes, suggesting that white holes may exist alongside their black counterparts under specific circumstances. Additionally, the idea of white holes is connected to discussions on wormholes. As previously mentioned, some theoretical physicists speculate that black holes could be linked to white holes through wormhole structures. The Einstein-Rosen bridge visualizes this connection, presenting a shortcut through spacetime that might link a black hole and a white hole. While these wormholes are also theoretical and fraught with challenges, including stability and traversability, this framework does stimulate ongoing research into the fabric of spacetime and how different types of singularities might interact. Finally, models involving quantum gravity propose processes that could lead to a renewed understanding of black hole thermodynamics and information. Some researchers suggest that, rather than erasing information when matter enters a black hole, it could be released through a white hole, offering a solution to the black hole information paradox. These theoretical models encourage a holistic view of the universe that intertwines black holes and white holes, emphasizing that further exploration of these concepts could deepen our understanding of the cosmos and the fundamental nature of reality. The concept of white holes introduces intriguing challenges to our understanding of thermodynamics and entropy, particularly in the context of black holes. In classical thermodynamics, the second law states that the entropy, a measure of disorder within a closed system, tends to increase over time. This principle suggests that processes naturally evolve towards states of higher entropy, reflecting the tendency toward disorder. Black holes present a unique challenge to this principle, since they can seemingly erase information and reduce entropy by absorbing matter and energy. If white holes were to exist, they would represent a process in which entropy might decrease locally as they expel matter and energy. This direct contradiction to the second law of thermodynamics creates a cognitive dissonance that challenges physicists to reconcile these laws with these hypothetical entities. If a white hole could release previously absorbed matter from a black hole, it raises questions about whether this expelled matter carries the original entropy, or if it somehow modifies the entropy of the universe as a whole. Moreover, the black hole information paradox adds complexity to this discussion. This paradox stems from the idea that information about matter consumed by a black hole seems to vanish, defying quantum mechanics, which asserts that information cannot be lost. If white holes were to serve as outlets for this lost information, they might provide a resolution to this paradox. The connection between black holes and white holes could imply that matter regains its status and reorganizes into a more ordered form upon ejection, effectively challenging traditional views of how entropy behaves across different systems. Furthermore, considering white holes in the context of cosmic evolution raises interesting possibilities regarding the life cycle of matter and energy in the universe. If white holes facilitate the connection between black holes and a broader cosmic structure, they prompt us to think about the long-term dynamics of entropy on a universal scale. Could the interplay between black and white holes allow for cycles of creation and destruction, leading to an ongoing balance of entropy throughout the cosmos? Such explorations enrich our understanding of the fundamental laws governing thermodynamics and could ultimately reshape our view of entropy as a dimensional feature of the universe rather than a strict, unbreakable law. Despite the intriguing theoretical frameworks surrounding white holes, there is currently no direct observational evidence supporting their existence. The notion of white holes arises from solutions to Einstein's field equations in general relativity, yet these solutions remain hypothetical without the direct observational data that we have for black holes. The challenge lies in the nature of white holes themselves. Since they are theorized to expel matter rather than absorb it, they would not emit detectable radiation like a black hole does. However, some astrophysicists have turned their attention to certain astronomical phenomena that could potentially be interpreted as evidence for white holes. One of these is the study of gamma-ray bursts, which are intense flashes of gamma rays observed in distant galaxies. Some researchers have speculated that these events could be linked to white hole activity, suggesting that they may represent the sudden expulsion of energy and matter from a white hole. This alignment with the hypothetical characteristics of white holes fuels further investigation, although it remains a contentious idea within the scientific community. Additionally, the existence of certain peculiar astronomical objects, like quasars or peculiar supernovae, has led some scientists to ponder whether they might be manifestations of white holes. Quasars, with their extraordinary luminosity and energy output, could be interpreted as remnants of matter expelled through a white hole. While these observations generate interesting hypotheses, they do not definitively provide evidence of white holes, but rather highlight the need for deeper understanding and further study. Ultimately, confirming or disproving the existence of white holes will likely require advancements in our observational capabilities and a more comprehensive grasp of the underlying physics. As our instruments become more sophisticated and our techniques improve, we may find ways to detect indirect signs that resonate with the characteristics of white holes, or we may be led in entirely new directions that enhance our understanding of the cosmos. Until then, the allure of white holes remains largely speculative, rooted in theoretical discussions rather than empirical evidence. Cosmic strings are fascinating theoretical objects predicted by various models in theoretical physics, particularly in the context of string theory and cosmology. They are essentially one-dimensional topological defects that may have formed in the early universe during phase transitions similar to those seen in other fields of physics. If they exist, cosmic strings would be extraordinarily thin, yet incredibly dense, with immense gravitational pull. Their unique properties might offer valuable insights into the nature of the universe and its structure. The formation of cosmic strings likely occurred shortly after the Big Bang, when the universe was cooling and undergoing significant changes. As different forces and fields settled into their permanent states, imperfections could have arisen in the fabric of space-time, leading to the creation of these strings. Once established, cosmic strings would stretch across vast distances, potentially spanning entire regions of the universe. Their presence could serve as gravitational anchors around which matter could accumulate, leading to the formation of galaxies and large-scale structures in the cosmos. One intriguing aspect of cosmic strings is their potential to influence our understanding of what lies beyond our observable universe. Because cosmic strings might extend beyond the limits of what we can see, they could serve as connections to regions of the universe that remain hidden from our direct observation. If they exist and are sufficiently long and massive, they could warp space-time around them, creating gravitational effects that might allow for the bending of light, an effect known as gravitational lensing. This could make it possible for us to observe phenomena that originate from portions of the universe we cannot directly access. Additionally, cosmic strings could provide a framework for exploring concepts such as multiple dimensions or higher dimensional spaces. They might help elucidate how various realms of the universe could interact or be connected, strengthening the case for theories like the multiverse. By examining these strings, researchers can probe questions about the structure and evolution of the cosmos on scales even larger than our observable limits. If cosmic strings exist, understanding their properties might help unlock the mysteries of the universe and guide us toward comprehending the broader realities that extend well beyond the boundaries of our perception. Cosmic strings are closely tied to the early formation of the universe, particularly within the framework of cosmological models that describe the events following the Big Bang. As the universe underwent rapid expansion and cooling, it experienced various phase transitions, similar to the behavior of materials changing states, such as from liquid to solid. During these transitions, fields that governed fundamental forces could have settled into different states, leading to the formation of topological defects, which include cosmic strings. The crucial moment for the creation of these strings is believed to have occurred during the symmetry-breaking phase transitions that happened in the very early universe. For instance, as the universe cooled, different forces could have separated or unified, creating regions where the symmetry of physical laws was no longer uniform. These imbalances might form cosmic strings, as the energy density within these regions causes them to stretch. Once created, these strings would be incredibly dense and possess strong gravitational fields. Cosmic strings could have significantly influenced the structure of the universe as it evolved. Their presence would act like gravitational scaffolding around which matter could cluster. This would lead to the development of galaxies and other cosmic structures as matter accumulated along the strings. Therefore, cosmic strings could provide a mechanism for explaining the uneven distribution of matter we observe in the universe today. By attracting and trapping mass, these strings could help create the large-scale structures of the cosmos more efficiently than gravity alone would accomplish. Additionally, the study of cosmic strings has implications for understanding the dynamics of the early universe and the interactions of different fields. They may also shed light on concepts like cosmic inflation, a period of rapid expansion that smoothed out the universe after the Big Bang. As researchers investigate the conditions and outcomes of such phase transitions, cosmic strings could provide a window into the fundamental processes that shaped our universe in those formative moments. Their potential existence points toward a deeper understanding of how the cosmos evolved and how complex structures emerged from simple beginnings. Domain walls are fascinating topological defects that can emerge in various field theories, including those relevant to cosmology. They are two-dimensional structures that occur when different regions of the universe exhibit distinct field values or phases. Similar to the way a phase transition can create boundaries between regions of differing states, such as ice and water, domain walls represent the surfaces where these differences manifest. In cosmological models, these walls can play a significant role in shaping the dynamics of the early universe and influencing the distribution of matter and energy. The formation of domain walls is often associated with symmetry-breaking phase transitions, where a field acquires a specific value that is not uniform throughout the universe. When this happens, regions with different vacuum states can develop, leading to the presence of a wall that segregates these domains. The boundary created by the domain wall typically has distinct physical properties compared to the regions on either side, often exhibiting unique energy densities and behaviors. This separation might impact the evolution of the universe by influencing how matter moves and interacts across different phases. As cosmologists explore the implications of domain walls, they consider how these structures might affect cosmic evolution. For example, domain walls can exert gravitational effects on the surrounding matter fields. They may act as barriers that influence how and where matter accumulates, potentially leading to non-uniformities in the density distribution of the cosmos. Consequently, they could help explain variations in cosmic structures, much like cosmic strings, albeit with different mechanisms of influence. Furthermore, if domain walls can separate different regions of space, they might lead to fascinating scenarios regarding the conditions and properties of those regions. For instance, one side of a domain wall could be governed by one set of physical laws or constants, while the other side might exhibit different characteristics. This relationship opens exciting avenues for exploring concepts such as the multiverse, where different regions of space could follow distinct physical rules. Such possibilities challenge our understanding of the universe and encourage deeper inquiries into the fundamental nature of reality and how various phases can coexist and influence one another throughout cosmic history. Cosmic strings and domain walls both represent intriguing possibilities for how our universe might connect with other universes, particularly within the framework of multiverse theories. Each of these structures could act as boundaries or gateways, facilitating interactions between different regions of space-time or potentially different universes altogether. Cosmic strings, being one-dimensional defects in space-time, could theoretically act as cosmic highways, extending far beyond our observable universe. If these strings exist, they might provide pathways through which matter and energy could be exchanged or transformed. Some hypotheses suggest that cosmic strings could connect to other topological defects or mathematical constructs, such as wormholes, potentially allowing for travel between different regions of space or even different universes. This connectivity could enable a form of transportation across vast distances, making seemingly distant regions accessible. On the other hand, domain walls, as two-dimensional structures that separate different vacuum states, may also function as barriers or gateways. These walls could establish boundaries between regions that obey different physical laws or fundamental constants. If such domains exist, transitioning across a domain wall might expose an observer to entirely different physical conditions. This provides a framework where two separate regions of space could experience varying realities, leading to the idea that domain walls might delineate distinct universes within a larger multiverse context. Both cosmic strings and domain walls, though primarily theoretical, prompt powerful questions about the nature of existence and our understanding of the cosmos. If we consider their roles as potential gateways, we must explore how their interactions might influence the properties of the universe as a whole. For instance, how would the presence of a cosmic string impact the gravitational dynamics around it? Or how might a domain wall dictate the kinds of interactions that occur on either side? These inquiries encourage a deeper engagement with the mysteries of the universe and highlight the interconnectedness of different regions or realities. Both structures challenge our perceptions of space and universality, engaging us in discussions about the roles they might play in connecting different parts of the cosmos and expanding our understanding of the nature of reality. Through this lens, cosmic strings and domain walls become not just abstract concepts, but potential keys to unlocking the insights behind the multiverse and the fundamental workings of our universe. To identify the presence of cosmic strings or domain walls, scientists would look for specific observational signatures that would be indicative of these theoretical structures. Each type of defect would produce distinct patterns in the cosmic microwave background radiation, gravitational lensing effects, and the distribution of large-scale structures across the universe. For cosmic strings, one of the most significant observational signatures would be the formation of specific gravitational lensing effects known as cosmic string lenses. These strings would create gravitational fields strong enough to bend light from distant objects, leading to unique visual distortions. This could result in the formation of rings or arcs around a string known as gravitational arcs. Researchers could potentially identify these effects by analyzing the light from background galaxies and seeking out patterns that cannot be explained by conventional lensing caused by more massive astronomical objects. Cosmic strings could also leave imprints in the cosmic microwave background radiation. As they interact with surrounding matter and energy, they might create slight temperature fluctuations in the microwave background, which scientists can measure. These fluctuations would manifest as non-Gaussian features, differing from the standard predictions of isotropy in the cosmic microwave background. Analyzing these patterns could provide an avenue for indirect detection of cosmic strings within the fabric of the universe's history. Domain walls, on the other hand, would be characterized by different signatures. If they exist, the presence of domain walls would likely influence density fluctuations in the universe. These walls could create regions of high energy density that affect galaxy formation and the large-scale distribution of matter. Observers may look for patterns in the large-scale structure of the universe, such as unexpected voids or anisotropies that correspond to the locations of domain walls. Additionally, domain walls may also generate effects in the cosmic microwave background, causing similar non-Gaussian signatures due to density perturbations. Scientists could search for sudden temperature changes across the background radiation, indicating that these walls had imprinted their characteristics onto the early universe. In conclusion, the search for cosmic strings and domain walls hinges on analyzing gravitational lensing phenomena, as well as examining the cosmic microwave background and large-scale structure of the universe for unique patterns. As our observational technology advances, researchers remain optimistic about identifying these signatures, which would deepen our understanding of the cosmos and the fundamental processes shaping it. The holographic principle is a thought-provoking concept in theoretical physics and cosmology that proposes a novel way of understanding the nature of space, time, and information. It posits that all the information contained within a volume of space can be represented as a two-dimensional surface that surrounds that volume. This idea suggests that our three-dimensional perception of the universe is, in a sense, an illusion, akin to a hologram that encodes the information on a two-dimensional plane. The principle emerged from considerations in black hole physics and string theory. In particular, researchers noted that black holes have a maximum amount of entropy directly related to the area of their event horizon, rather than the volume enclosed. This relationship hinted that the information about the contents of a region of space might be encoded on its boundary. This implies that everything we experience in 3 dimensions could be viewed as arising from information hidden on a 2-dimensional surface, thereby fundamentally altering our grasp of dimensions and reality. By reframing our understanding of the universe through the lens of the holographic principle, new perspectives on gravity and quantum mechanics emerge. It offers a potential reconciliation of these two fundamental areas of physics, which have traditionally struggled to coexist within a single framework. This is particularly salient in the context of black holes, where questions about the fate of information that falls into them often arise. The holographic principle suggests that this information is not lost, but rather encoded on the surface of the black hole, which may eventually be released back into the universe, preserving the idea that information remains constant. Additionally, the The holographic principle encourages exploration of concepts like space-time and dimensionality, leading to a deeper understanding of the fabric of the universe itself. It raises fundamental questions about what reality really is and challenges our perceptions of existence. Are we merely perceiving an intricate projection of deeper dimensional information? In this way, the holographic principle offers a unique perspective on the interplay between information, reality, and the fundamental laws of nature, prompting ongoing research and theoretical exploration as scientists strive to grasp its implications for our universe and the cosmos at large. The holographic principle suggests that our universe operates as a kind of projection from a higher dimensional space, fundamentally altering our perceptions of reality and existence. This idea arises from the notion that the information contained within a three-dimensional region of space can be represented on a two-dimensional surface that bounds that region. By extending this thought experiment, researchers postulate that our familiar three-dimensional universe could be a manifestation of information encoded in a higher dimensional framework. If our universe is seen as a hologram, it signifies that the complexity and richness of our three-dimensional experience can be derived from underlying processes or structures existing in a higher dimensional space. For instance, this conceptualization echoes insights derived from string theory, which posits that the universe could be composed of tiny, vibrating strings existing in multiple dimensions beyond the familiar three. If the holographic principle holds true, then the entire fabric of space-time and its physical laws could emerge from interactions occurring in these additional dimensions. One interesting consequence of this perspective relates to the nature of gravity and quantum mechanics. Traditional understandings of gravity arise from a three-dimensional viewpoint, complicating the reconciliation of gravity with quantum principles. However, if the holographic principle is valid, it might imply that gravitational interactions are manifestations of deeper, more fundamental processes occurring in a higher dimensional realm. This could pave the way for a more unified understanding of the fundamental forces of nature, allowing physicists to bridge the gap between the description of gravity and the discrete behaviors observed at the quantum level. Furthermore, the idea that our universe is a projection from a higher dimensional space prompts existential questions about the nature of reality itself. If perceptions of space and time can be considered emergent phenomena rather than fundamental truths, it opens up possibilities for re-evaluating concepts such as causality, existence, and what it means to live within a universe. It encourages researchers to investigate the implications of dimensionality and information theory, fostering a rich interplay between cosmology, quantum mechanics, and philosophy. The holographic principle offers a revolutionary framework for understanding our universe as a projection emerging from higher dimensional realities. This perspective challenges existing paradigms and inspires new inquiries into the nature of existence, potentially leading us closer to comprehending the underlying structure of the cosmos and the forces that govern it. The holographic principle carries profound implications for our understanding of what exists beyond our observable universe. By suggesting that our three-dimensional reality is a projection of information encoded on a two-dimensional surface, it opens up intriguing possibilities regarding the nature of space, time, and the boundaries of our universe. One fundamental implication is that the universe might extend far beyond what we can currently observe, with regions of space that are fundamentally linked through deeper, higher dimensional structures. If our universe is indeed a holographic projection, the areas beyond our observable limits could be governed by the same underlying laws that we recognize within our visible sphere. This suggests that there are additional regions that might contain distinct physical phenomena, potentially operating under similar or entirely different conditions. Rather than seeing the observable universe as a complete entity, the holographic principle encourages us to consider it as a fragment of a much larger, interconnected cosmic tapestry that transcends our current observational capabilities. Such a perspective also generates questions concerning the nature of causality and the flow of information in the universe. If the information that describes our universe can be encoded on boundaries, then changes or events in distant regions of the cosmos may still have implications for our observable universe, albeit indirectly. This interconnectedness might allow for patterns or phenomena in the universe that we cannot directly measure, but could affect our understanding through the influence of distant regions or higher dimensional structures. The holographic principle could also lead to reconsiderations of the nature of dark energy and dark matter. If much of what we term dark aspects of the universe arises from higher dimensions, their properties and behaviors might be better understood through the lens of holographic relationships. This transforms the quest for understanding dark matter and dark energy from merely identifying particles or fields to exploring the deeper geometric and informational fabric of the universe that encodes and manifests these elusive phenomena. Ultimately, embracing the holographic principle challenges traditional views on the boundaries of our universe, emphasizing that what exists beyond our observable limits might be just as significant as what we can currently measure. It invites speculation about the nature of reality itself and encourages an exploration of higher dimensional spaces that might hold secrets about the underlying dynamics shaping our universe. By thinking beyond the observable, we confront the possibility of a far richer and more complex cosmos than our current observations might indicate. The holographic principle is deeply intertwined with both string theory and the quest for a theory of quantum gravity, offering important insights into the nature of space-time and the fundamental forces of the universe. At its core, string theory posits that the basic building blocks of the universe are not point-like particles, but rather tiny, vibrating strings existing in multiple dimensions. This framework inherently aligns with the ideas of the holographic principle, as both approaches challenge traditional understandings of space and reality. In string theory, higher dimensions beyond the familiar three of space and one of time are not merely theoretical constructs, they are essential for the consistency of the theory. The holographic principle complements this framework by suggesting that the information contained in a volume of space can be encoded on its boundary, which might be represented by a two-dimensional surface in these higher dimensions. The idea that our three-dimensional universe could emerge from the data residing on a two-dimensional holographic screen resonates well with string theory's multidimensional nature. Essentially, this proposes that all the rich complexities of particle interactions and the fundamental forces are emergent properties arising from more foundational layers of reality. Moreover, the holographic principle provides potential resolutions to some of the problems encountered when trying to reconcile quantum mechanics and general relativity, such as the black hole information paradox. In the context of string theory, the holographic principle implies that information swallowed by black holes may not be lost, but rather is stored on the event horizon of the black hole. This suggests a way for quantum mechanics to remain consistent even in the face of the extreme conditions surrounding black holes, thus bridging the gaps between the two theories. String theory also offers a framework to explore higher dimensional phenomena, such as additional spatial dimensions that can influence gravitational behavior. The holographic principle fits into this picture by highlighting how gravitational degrees of freedom can be fundamentally linked to quantum information. This connection hints that our understanding of gravity itself might be an emergent phenomenon derived from more fundamental quantum processes. The holographic principle relates to string theory and quantum gravity by proposing that our three-dimensional reality is an emergent projection from a higher dimensional framework where information is encoded on boundaries. This relationship opens up avenues for resolving fundamental questions about the universe, suggesting that deeper understanding of gravity, space-time, and quantum mechanics may lie in exploring these connections among higher dimensional structures, information theory, and the holographic nature of existence itself. The holographic principle suggests that our three-dimensional reality could be encoded on a two-dimensional surface. This intriguing idea has found some experimental support over the years, particularly through studies related to black holes and the nature of quantum gravity. One of the key pieces of evidence comes from the study of black hole thermodynamics. Stephen Hawking's groundbreaking work showed that black holes possess entropy, and this entropy is proportional to the area of their event horizons rather than their volume. This finding hints at the idea that all the information contained within a three-dimensional space can, in some way, be captured on a two-dimensional boundary. Another significant line of evidence comes from string theory and its implications for quantum gravity. Calculations involving certain string theory models show that the behavior of gravity and the fundamental forces can be described in a holographic context. For instance, researchers have explored two-dimensional models that exhibit features of four-dimensional space-time, providing theoretical groundwork that supports the holographic view of the universe. The ADS-CFT correspondence, which describes a relationship between theories of gravity in a higher dimensional space and strong coupling quantum field theories in lower dimensions, has bolstered this idea further. More recently, scientists have turned their attention to the cosmic microwave background radiation. By studying the patterns and fluctuations in this relic radiation from the early universe, researchers have begun to see hints that might align with holographic principles. Such investigations aim to uncover whether the large-scale structure of the universe can be traced back to two-dimensional information encoded at its boundaries. These experimental observations and theoretical developments create a tapestry of evidence that supports the holographic principle. While the concept remains a subject of intense research and debate, the intriguing interplay between gravity, black holes, and quantum mechanics continues to push the boundaries of our understanding of reality. Each discovery brings us closer to unlocking the mysteries of the universe and challenging our traditional notions of space and dimension. The theory of eternal inflation is a groundbreaking concept in cosmology that expands upon the initial moments of the universe's existence. According to this theory, the rapid expansion of the universe, known as inflation, does not end uniformly across all regions. Instead, some areas continue to inflate while others stop, leading to the formation of pockets of space where inflation has ceased. This ongoing process gives rise to an ever-expanding multiverse filled with numerous distinct universes, each with its own set of physical laws and constants. Eternal inflation proposes that the universe we observe is just one part of a much larger cosmic landscape. As inflation persists, new regions are continually created, branching off from the original inflating field. Each of these regions experiences different conditions, which can lead to the development of separate universes. Some of these universes may resemble our own, while others might have entirely different physical properties, creating an astonishing diversity of possible realities. Current cosmic structures, such as galaxies and stars, formed in regions where inflation ended, allowing for the emergence of the universe we inhabit today. Meanwhile, in the regions that remain in a state of inflation, the laws of physics as we know them may not apply. This idea reshapes our understanding of the universe, suggesting that rather than a single universe with a defined history, we might inhabit one of countless universes that exist simultaneously. The notion of eternal inflation not only addresses some key questions in modern cosmology, such as the uniformity of the universe's structure and the observed fluctuations in the cosmic microwave background radiation, but it also opens the door to profound philosophical implications. As we ponder the vast multiverse, we confront questions about the nature of reality, existence, and our own place within this complex tapestry of universes. Each step forward in understanding eternal inflation helps unravel the mysteries surrounding the beginning and the breadth of the cosmos. Eternal inflation builds upon the foundations of the standard inflationary model, but introduces significant differences that reshape our understanding of the universe's expansion. The standard inflationary model posits that a brief period of rapid exponential expansion occurred in the very early universe, roughly between 10 to the minus 36 seconds to 10 to the minus 34 seconds after the Big Bang. This rapid inflation resolved various issues such as the flatness problem, the horizon problem, and the absence of magnetic monopoles, providing a scenario where the universe became uniformly hot and dense, leading to the large-scale structure we observe today. In contrast, eternal inflation suggests that this inflationary phase does not end uniformly across the universe. While some regions stop inflating and give rise to the observable universe, other regions continue to inflate indefinitely. Consequently, rather than a single event that concludes, the universe experiences a perpetual process of expansion, leading to a multitude of distinct regions or pocket universes, each with its unique properties. This distinction is crucial because it introduces the concept of a multiverse, where a vast collection of universes exists simultaneously, each potentially governed by different sets of physical laws. The implications of eternal inflation extend beyond merely positing multiple universes. It offers a dynamic framework through which our universe is but one bubble in an ongoing inflationary process. Each bubble can evolve independently after inflation ceases, leading to diverse phenomena and evolutionary paths. This scenario contrasts with the Standard Model, which assumes homogeneity and isotropy in the aftermath of inflation, limiting the universe's evolution to that singular energetic event. Eternal inflation also raises profound questions about the fundamental nature of reality and our understanding of cosmology. By suggesting that the inflating regions are continually forming and never fully ceasing, it complicates our understanding of the universe's initial conditions. As researchers delve deeper into both inflationary models, they uncover opportunities to explore the very nature and fabric of existence, pushing the boundaries of what we know about our cosmos. In the context of eternal inflation, bubble universes refer to regions of space that have stopped the rapid inflationary expansion and have developed into distinct, self-contained universes. As the inflationary process continues in certain areas, other regions cease to inflate and cool down. This leads to the formation of these bubbles, which can expand and evolve independently from one another. Each bubble universe can have its own unique physical properties, constants, and even laws of physics, reflecting the diverse conditions present in the different regions of the inflating cosmos. The concept of bubble universes illustrates a crucial aspect of eternal inflation, where the universe is not a singular entity that began and ended in a defined event. Instead, it proposes a multiverse scenario where our observable universe is merely one bubble amidst countless others in an ever-expanding landscape. Each of these bubbles might contain various structures such as galaxies and stars, shaped by unique initial conditions and physical laws that govern their development. One fascinating aspect of bubble universes is that they can differ significantly from each other. For example, one bubble may exhibit properties and conditions similar to our own universe, while another could have entirely different fundamental forces, particle types, or even dimensional structures. This diversity stems from the varying conditions in the inflating field that leads to each bubble's formation. Some might even remain uninhabitable due to extreme conditions or other limiting factors. The study of bubble universes raises intriguing questions about the nature of reality and the fundamental understanding of our universe. If these distinct regions exist, it opens up philosophical and scientific inquiries regarding the nature of existence, the meaning of fine-tuning in physical constants, and the potential for life in other universes. As physicists and cosmologists continue exploring the implications of eternal inflation and its associated bubble universes, they delve deeper into the complexities of the cosmos and our place within it. Eternal inflation creates a framework where the process of cosmic expansion never truly ends, leading to the possibility of an infinite number of distinct universes. In this scenario, while certain regions of space undergo inflation for a limited period and eventually transition into a cooling state, other regions continue inflating indefinitely. This ongoing activity forms an ever-growing landscape of separate bubbles, where each bubble represents a unique universe. As inflation persists in various regions, it generates countless bubble universes over time. Each bubble occupies its own section of the inflating cosmos and develops independently of the others. This means that as long as inflation continues in specific areas, new bubbles can arise constantly, contributing to an unbounded and potentially infinite collection of universes. Each new universe could be characterized by different physical laws, constants, and initial conditions, leading to a vast array of possible realities. The notion that eternal inflation can produce an infinite number of universes is essential to understanding the implications of the multiverse theory. Since each bubble can have its own distinct properties, some universes may resemble our own, while others could diverge dramatically. This variability is rooted in the randomness inherent in quantum fluctuations during the inflationary process, leading to a wide range of outcomes. For instance, some bubbles may support life, while others may be inhospitable or even entirely devoid of matter. Moreover, the concept of eternal inflation assures that new bubbles can continuously form even if previously created bubbles stop inflating. This characteristic means that the number of universes could grow endlessly. As researchers explore the ramifications of this model, they encounter profound philosophical questions about existence and the nature of reality. Eternal inflation not only reshapes our understanding of the universe, but also invites us to contemplate a multiverse that stretches far beyond our observed cosmos, each universe a unique reflection of a vast and intricate process. Observational evidence specifically supporting the theory of eternal inflation is still a matter of ongoing research and debate. However, there are various indirect pieces of evidence and phenomena that align with the ideas presented by eternal inflation. One key area of inquiry revolves around the cosmic microwave background radiation, which serves as a remnant of the early universe. The tiny fluctuations observed in this radiation provide insights into the conditions that existed shortly after the Big Bang, and some of these patterns could reflect the consequences of an inflationary phase. The statistics of temperature fluctuations in the cosmic microwave background have been studied extensively, revealing a nearly uniform temperature across the sky, punctuated by slight irregularities. These anomalies could be interpreted as the imprint of inflationary dynamics, which would have smoothed out the universe. The underlying mechanisms proposed in eternal inflation suggest that such patterns may arise from quantum fluctuations amplified during the inflationary phase, supporting the idea that our universe underwent a rapid expansion. Additionally, researchers have considered the implications of eternal inflation in connection with the large-scale structure of the universe. The distribution of galaxies and clumps of matter shows remarkable uniformity. The statistics of temperature fluctuations in the cosmic microwave background have been studied extensively, revealing a nearly uniform temperature across the sky, punctuated by slight irregularities. These anomalies could be interpreted as the imprint of inflationary dynamics, which would have smoothed out the universe. The underlying mechanisms proposed in eternal inflation suggest that such patterns may arise from quantum fluctuations amplified during the inflationary phase, supporting the idea that our universe underwent a rapid expansion. Additionally, researchers have considered the implications of eternal inflation in connection with the large-scale structure of the universe. The distribution of galaxies and clumps of matter shows remarkable uniformity, suggesting that gravitational influence was exerted uniformly during the early expansion phase. This evidence indicates that processes consistent with eternal inflation could have produced the conditions necessary for such structures to arise, as gravitational effects evolve in different bubble universes. The search for primordial gravitational waves represents another exciting avenue for evidence in support of eternal inflation. If gravitational waves existed during the inflationary period, they could have left detectable signals, such as tensor modes, in the cosmic microwave background. Although researchers have yet to definitively observe these gravitational waves, their potential existence would lend considerable weight to the inflationary framework, further bolstering the hypotheses surrounding eternal inflation. As scientists continue to investigate these areas, the cumulative data may eventually paint a clearer picture regarding the validity of eternal inflation. Although conclusive observational evidence remains elusive currently, the connections to cosmic phenomena and large-scale structures offer compelling avenues to explore the complex interplay between inflationary dynamics and the evolution of our universe. The cyclic model of the universe proposes that the cosmos undergoes an infinite series of expansions and contractions creating an eternal cycle of big bangs followed by big crunches. In this framework, rather than originating from a singular event approximately 13.8 billion years ago, the universe continuously evolves through these cycles. Each cycle begins with a big bang, leading to expansion, and eventually culminates in a contraction phase where the universe collapses back into a singularity, only to rebound in another big bang, thus restarting the cycle. This model challenges the traditional Big Bang theory, which presents the universe as having a singular beginning marked by the explosion of space from an incredibly hot and dense state. The Big Bang theory implies a finite history, indicating that the universe has been expanding since that original event without the possibility of a reversal into a crunch. In contrast, the cyclic model suggests that time is infinite, and the universe does not have a definitive beginning or end. Instead, it emphasizes a more dynamic and eternal view of cosmic evolution. One of the driving concepts behind the cyclic model is the interplay between gravity, dark energy, and other forces at work in the universe. As the universe expands, the effect of dark energy becomes more significant, potentially leading to a phase of acceleration. Ultimately, the theory proposes that this acceleration may be temporary, followed by gravitational forces dominating to initiate the contraction phase. This cycle would repeat indefinitely, presenting a fundamentally different perspective on the nature of cosmic events compared to the static one of the Big Bang theory. Several variations of the cyclic model, including those informed by string theory, have emerged to address various issues raised by the conventional understanding of the universe. This approach seeks to provide insights into the behavior of cosmic structures and the nature of inflation, while simultaneously addressing the fate of the universe. By proposing a model in which the universe is in a perpetual state of rebirth, the cyclic view invites further exploration of fundamental questions regarding time, space, and the cosmic evolution we observe today. The ekpyrotic scenario presents an alternative view of cosmic creation and evolution, positing that our universe originated from the collision of two three-dimensional brains in a higher dimensional space. Rather than emerging from a singularity in a traditional Big Bang event, this model suggests that the universe evolved from a series of interactions between these brains. The term ekpyrotic derives from the ancient Greek word for conflagration, reflecting the idea that the collision could create a highly energetic event, resulting in the conditions necessary for our universe to develop. In this framework, the two brains are thought to exist within a higher dimensional space, referred to as the bulk. These brains are not just flat surfaces, but can contain matter and energy. When two such brains collide, the interaction generates immense energy and sets off an expansion similar to that of inflation, providing a context for the observable universe to evolve. The ekpyrotic model neatly explains how physical properties and processes could have been influenced by the characteristics of the brains and their collision dynamics. The evolution of the universe in the ekpyrotic scenario also proposes substantial differences compared to the conventional Big Bang model. Instead of a singular moment of creation, the universe experiences cyclical collisions involving various brains. These recurring events create an ongoing process of cosmic dynamics, where each collision might lead to a new phase of expansion and contraction, shaping the universe's structure over time. This ongoing cycle allows for an adaptable and evolving system, in contrast to a universe that simply expands from a single origin. A significant aspect of the ekpyrotic scenario is its ability to address certain issues encountered in traditional cosmological models, such as the flatness and horizon problems. The interactions between brains could naturally lead to a homogeneous and isotropic universe without invoking an abrupt inflationary period. As researchers explore the implications of this model, they seek to better understand the fundamental principles guiding the universe's creation and evolution, challenging our conventional understanding and exploring the potential interplay between higher dimensions and cosmic phenomena. Brains play a fundamental role in both the cyclic and ekpyrotic models, serving as the building blocks of the universe and facilitating the dynamics that explain cosmic evolution in these frameworks. In string theory, branes are multi-dimensional objects that can exist in higher dimensional spaces, providing a versatile foundation for exploring the structure of the universe beyond traditional three-dimensional perspectives. In both the cyclic and ekpyrotic scenarios, branes are central to the processes that generate cosmic phenomena. In the context of the ekpyrotic model, two branes inhabit a higher dimensional space, often referred to as the bulk. When these two branes collide, the energy released during this interaction initiates a new phase of expansion, setting the conditions for the universe we observe today. This collision is not merely a one-time event. Instead, it can happen repeatedly over time, leading to a cyclical process where each collision creates a new phase of the universe's evolution. This perspective offers a way to visualize cosmic creation that integrates principles from higher dimensional physics and helps explain the characteristics of our universe without invoking a singular initial explosion. Similarly, in cyclic models, branes serve as essential components that facilitate the interactions between different regions of the universe. The concept begins with the idea that our universe exists on one brane, while other branes interact with it in the higher dimensional space. The collisions between these branes can cause the universe to enter different phases of expansion and contraction, resulting in a series of big bangs and big crunches. Each collision can reshape the universe, allowing it to transition seamlessly from one state to another and creating a dynamic, ever-evolving system. The relationship between branes and the neighboring dimensions opens up intriguing possibilities regarding the fate and evolution of the universe. By providing a mechanism for interactions that generate energetic conditions necessary for cosmic evolution, these higher dimensional objects challenge conventional views of a singular beginning and present an ongoing process in which the universe can transform continuously. As theories evolve, the exploration of branes enriches our understanding of the fundamental forces shaping the cosmos, inviting consideration of how higher dimensional physics interfaces with our three-dimensional experience. The cyclic and ekpyrotic models provide intriguing insights into what may have existed before our universe and what lies beyond its current state. These frameworks reject the notion of a singular beginning in favor of an ongoing cosmic process, suggesting that the universe is part of a larger, more complex reality. In the cyclic model, the universe is depicted as undergoing endless sequences of expansion and contraction. This implies that there was no definitive moment when the universe began. Rather, it is part of an infinite series of cycles. Each cycle might have stages involving different physical laws and conditions. Therefore, before our current universe, there could have been a preceding universe that contracted into a singularity, only to rebound in another Big Bang event. The cyclic nature of this model challenges the conventional idea of time and existence, positing that the universe has always been part of this eternal rhythm. The ekpyrotic model offers a different perspective by suggesting that our universe emerged from the collision of two branes in a higher dimensional space. In this scenario, the existence of the branes themselves implies that there are dimensions and structures beyond our familiar three-dimensional universe. The space where these branes reside could be filled with multiple branes and other higher dimensional objects, creating a rich tapestry of potential interactions. This higher dimensional environment allows for the possibility that there were entities or structures that existed prior to our universe, giving rise to our cosmos through the dynamics of brane collisions. In both frameworks, the question of what lies beyond our universe is viewed through the lens of higher dimensions and cyclic interactions. There may be many more universes or branes existing parallel to ours, each with its unique set of physical laws and histories. Rather than a well-defined edge or boundary to our universe, these models suggest a vast multiverse in which different regions may operate under varying principles, presenting the potential for a multitude of cosmic realities. These ideas prompt valuable discussions about the nature of existence, time, and the fundamental framework governing the cosmos. The cyclic and ekpyrotic models reflect a desire to understand reality beyond the confines of a singular origin story, opening avenues for exploration into the deeper mysteries of the universe's evolution and what it means for both its past and future. Support for the cyclic and ekpyrotic models of the universe primarily comes from indirect observational evidence rather than definitive proof. Researchers have focused on various cosmic phenomena, looking for patterns or characteristics that align with the predictions made by these models. One of the core areas of interest is the cosmic microwave background radiation, which carries significant information about the early universe. In the ekpyrotic scenario, the collisions of brains can leave specific imprints in the cosmic microwave background. These imprints might manifest as unusual temperature fluctuations or anomalies in the cosmic microwave background that differ from what classical inflationary models predict. Some researchers have analyzed the statistical distribution of these fluctuations to identify signatures consistent with collision events, though clear evidence remains a topic of investigation and debate. The cyclic model also seeks to address certain challenges faced by the inflationary model. For example, some predictions regarding the uniformity and isotropy of the cosmos can be examined through the large-scale distribution of galaxies and cosmic structures. The patterns of galaxy clustering could reflect the effects of repeated cycles of expansion and contraction. Certain alignments or distributions observed may suggest that our universe underwent prior cycles, though the relationship to cycling remains complex. Moreover, gravitational waves generated during early cosmic expansion could provide critical data supporting these models. If the ekpyrotic or cyclic scenarios are correct, they may predict the existence of specific types of gravitational waves resulting from brane collisions or interactions. While gravitational wave astronomy is still in its early stages, detecting these signals could lend significant weight to the cyclic and ekpyrotic frameworks. Currently, both models continue to be tested through observations of the universe and the nature of the cosmic background radiation. While hard evidence remains elusive, the search for patterns, fluctuations, and gravitational waves presents exciting opportunities for gathering data that could either support or challenge these alternative models of cosmic evolution. As observational technologies improve and theories evolve, the understanding of these complex models may broaden, revealing deeper insights into the nature of the universe. Quantum cosmology is a field that seeks to apply the principles of quantum mechanics to the entire universe, aiming to understand its origins and fundamental nature through a quantum lens. Traditional cosmology often relies on classical physics and general relativity to describe the universe's structure and evolution, but quantum cosmology introduces the idea that the universe itself may have quantum properties that are essential for understanding its beginnings and dynamics. One of the main goals of quantum cosmology is to address the question of what came before the Big Bang. Traditional models struggle with the concept of singularities, points where densities become infinite, such as the initial state of the universe. Quantum cosmology aims to resolve these singularities by considering the universe's wave function, a mathematical description of its quantum state over time. This wave function encompasses all possible configurations of the universe, offering a probabilistic approach to cosmology. A prominent approach within quantum cosmology is the proposal of a no-boundary condition, introduced by physicist Stephen Hawking and his colleagues. This concept suggests that the universe's geometry is finite but without boundaries, akin to the surface of a sphere. According to this view, as the universe transitions from a quantum state to a classical one, it smooths out the singularities associated with the Big Bang, allowing for a more coherent understanding of its origins. Additionally, quantum cosmology explores the idea of multiple histories or paths through which the universe could evolve. Inspired by the principles of quantum mechanics, where particles can exist in superpositions of different states, quantum cosmology posits that the universe could follow various trajectories. These trajectories can lead to different physical scenarios, suggesting a richness and complexity to the universe's development that goes beyond deterministic models. By merging concepts from quantum mechanics with cosmology, this field attempts to deepen our understanding of the universe's origins, structure, and underlying laws. Quantum cosmology not only aims to provide answers to fundamental questions about existence, but also bridges the gap between the microscopic world governed by quantum phenomena and the vast cosmic scale of the universe. As researchers continue to refine their approaches and gather experimental evidence, quantum cosmology holds the potential to reshape our comprehension of reality itself. The Wheeler-DeWitt equation is a fundamental element in quantum cosmology, serving as a key equation that describes the quantum state of the universe. Developed by physicists John Archibald Wheeler and Bryce DeWitt in the 1960s, this equation emerges from attempts to merge quantum mechanics with general relativity, specifically in the context of the entire universe rather than individual particles. The equation aims to encapsulate the dynamics of the universe at its most fundamental level, addressing how space and time themselves behave in a quantum framework. A significant aspect of the Wheeler-DeWitt equation is that it operates within a realm where conventional notions of time and space break down. The equation describes a wave function for the universe, representing all possible configurations of the universe's geometry and matter. This wave function is essential for understanding how different states evolve, which links to the notion of multiple universes. In quantum mechanics, particles can exist in superpositions of states, suggesting that similar principles could apply to the universe itself. The relationship to multiple universes arises through the interpretation of the wave function produced by the Wheeler-DeWitt equation. Each solution to the equation can represent a different universe within a larger multiverse context. When considering various configurations of space, time, and matter, the wave function can populate a vast landscape of possibilities. This means that the act of observation or measurement in this framework could lead to collapses of the wave function that result in distinct outcomes, effectively creating branches in which different universes exist simultaneously. This idea dovetails with the concept of the many worlds interpretation of quantum mechanics, where every potential outcome of a quantum event occurs in a separate, branching universe. In this sense, the Wheeler-DeWitt equation may suggest a multiverse, a collection of coexisting, parallel universes arising from different solutions and arrangements. Each universe's state can be thought of as part of a vast cosmic tapestry woven from the fundamental dynamics and interactions encapsulated within the equation. By providing a mathematical foundation for understanding the universe in a quantum context, the Wheeler-DeWitt equation contributes significantly to discussions about the origins of the universe and the possibility of multiple universes. Ongoing research in this area continues to delve into the implications of this equation, further exploring the nature of reality and the underlying principles that govern the cosmos. The wave function of the universe is a concept in quantum cosmology that represents the quantum state of the entire universe. It describes all possible configurations of the universe's geometry, matter, and energy at a given time. This wave function emerges from the application of quantum mechanics to the universe as a whole, particularly through the Wheeler-DeWitt equation, which treats the universe in a manner similar to how quantum mechanics describes particles and systems. This wave function encapsulates every conceivable state the universe might occupy, functioning as a probabilistic distribution of outcomes rather than a single deterministic path. Because the universe's wave function contains all potential histories and structures, it allows for the possibility of different realities and scenarios existing simultaneously. When a measurement or observation occurs, the wave function can collapse, resulting in one particular outcome that corresponds to our observed reality, while other possibilities could manifest in parallel forms or branches. The implications of this wave function extend to the idea of multiple universes or a multiverse. Each solution to the wave function could correspond to a different universe with varying physical laws, constants, and initial conditions. In this way, worlds that differ from our own might coexist, potentially responsive to the same underlying quantum framework. These alternate realities may possess unique characteristics, shapes, or forms based on the probabilistic nature of the wave function and the variety of configurations it encompasses. Exploring the wave function of the universe leads to profound questions about existence and the nature of reality. If multiple universes emerge from various outcomes of the wave function, it opens up avenues for investigations into what these realities might look like and how they could interact or remain isolated from one another. This framework encourages a broader understanding of existence, suggesting that our observed universe is just one slice of a far more intricate cosmic structure. The concept of the wave function of the universe challenges our traditional notions of space, time, and reality, inviting contemplation about the vastness of potential existence beyond what we can observe. As researchers continue to grapple with the implications of this concept, the pursuit of understanding the universe's quantum foundations reveals a rich tapestry of possibilities just waiting to be explored. Quantum cosmology presents a novel approach to the problem of time in the early universe, a challenge that arises primarily from the limitations of traditional physics when applied to cosmic conditions. In classical general relativity, time is treated as a continuous linear progression that flows uniformly. Yet this perspective becomes complicated near singularities, such as the one proposed at the beginning of the universe during the Big Bang. At these extremes, conventional notions of time break down, leading to the question of what time even means in that context. One of the critical ways that quantum cosmology addresses the problem of time is through the concept of the wave function of the universe, particularly as described by the Wheeler-DeWitt equation. This equation does not include time as an independent variable in the same manner as classical theories. Rather, it treats the universe's state as a function of its geometry and matter configurations. This treatment implies that time may not exist as a fundamental feature in the early universe, but could emerge from underlying quantum processes instead. In this view, time is not an absolute backdrop against which events unfold, but rather a relational aspect that arises from the interactions and relationships between quantum states. Additionally, the no-boundary proposal introduced by Stephen Hawking offers valuable insights into the nature of time at the universe's origin. This model suggests that the universe has no boundaries in the traditional sense, allowing time to be smooth and finite while avoiding singularities. Instead of a sharp demarcation marking the beginning of time, the early universe can be viewed as a sort of quantum foam, where traditional concepts of time and space blend together. This approach establishes a framework in which time can emerge from the collapse of the wave function into distinct states and futures as the universe evolves. Furthermore, quantum cosmology opens up the possibility of multiple histories or trajectories, where different timelines can arise from various quantum states. Each of these timelines could represent a distinct way the universe might develop, challenging our linear understanding of time. In this interpretation, time is contingent upon the evolution of the universe's wave function and its associated dynamics, highlighting a more complex relationship between events rather than a simple progression. Through these frameworks, quantum cosmology approaches the enigmatic problem of time, suggesting that it may not be a fundamental aspect of the universe, but rather a secondary property emerging from deeper quantum realities. This perspective not only advances our understanding of the early universe, but invites further philosophical inquiry into the essence of time itself and its role in the fabric of reality. Testing quantum cosmology theories lends itself to a fascinating blend of empirical observations and intricate experiments that probe the very fabric of our universe. One area of significant interest is the study of cosmic microwave background radiation. This remnant of the Big Bang contains crucial information about the early universe's conditions. Anomalies in the temperature fluctuations can offer insights into quantum effects that may have happened during the birth of the cosmos, potentially validating quantum gravity theories. Another promising avenue is the exploration of gravitational waves. These ripples in spacetime, first detected in 2015, are produced by some of the universe's most energetic events, such as black hole mergers or neutron-star collisions. Analyzing these waves helps scientists understand the quantum properties of gravity, especially during extreme conditions where traditional physics might break down. The detection and measurement of gravitational waves can provide clues on how quantum mechanics operates on a cosmological scale. Moreover, experiments attempting to observe primordial quantum fluctuations offer yet another layer of validation for quantum cosmology models. These fluctuations are thought to be responsible for the large-scale structure of the universe we see today. If researchers can detect these fluctuations, perhaps through the sensitive instruments that measure the distribution of galaxies or the density variations in the cosmic microwave background, it would bolster the argument that quantum principles influence the universe's earliest moments. Finally, future technological advances, such as those in quantum computing and high-energy particle physics experiments, may also contribute essential insights. These tools could help simulate early universe conditions, explore fundamental particles, and reveal the connections between quantum mechanics and gravitational forces. As our observational technologies improve, the boundaries of quantum cosmology will continue to expand, inviting scientists to uncover deeper truths about the universe's birth and evolution. Black holes have long captured the imagination of scientists and the public alike, serving as mesmerizing enigmas in our understanding of the cosmos. One of the most captivating theories suggests that black holes might serve as gateways to other universes or regions beyond our own. This concept often involves the idea of wormholes, hypothetical tunnels in space-time that might connect distant parts of the universe, or even different universes entirely. Imagine a shortcut through the cosmos, where the trek of millions of light-years could be reduced to an instant by navigating through a wormhole formed by a collapsing star. In theoretical physics, specific models propose that when matter falls into a black hole, it could create a bridge to another point in space-time. This is often described in terms of the Einstein-Rosen bridge, which arises from the equations of general relativity. While this mathematical framework suggests the possibility of such connections, the practicalities remain hazy. The chaotic environments and extreme gravitational forces near black holes could present insurmountable challenges, making it unclear if anything could survive a journey through such regions. Moreover, the notion of a black hole leading to a different universe raises questions about the nature of reality itself. The multiverse theory, which posits the existence of multiple, perhaps infinite universes, complements this idea. Should black holes act as portals, they might connect our universe with others that contain different physical properties, constants, or dimensions, leading to a wealth of possibilities beyond what we can currently imagine. However, the current understanding of black holes suggests that any information or matter crossing the event horizon is likely lost to the outside universe, leading to the so-called black hole information paradox. Researchers are exploring concepts such as holographic principles and quantum entanglement to reconcile these ideas. As studies continue and theoretical models evolve, black holes will remain a focal point for understanding the complexities of our universe and the tantalizing possibility that they might connect us to realms beyond our own. The black hole information paradox is a profound dilemma in theoretical physics that arises from the interplay between quantum mechanics and general relativity. At its core, the paradox questions what happens to information when it falls into a black hole. According to quantum mechanics, information cannot be destroyed. This principle ensures that the state of a quantum system can always be deduced from its outcomes. However, when matter crosses the event horizon of a black hole, it seemingly becomes irretrievable. As the black hole evaporates over time due to Hawking radiation, the question arises, has the information about what fell in been lost forever, or does it somehow escape? This paradox has prompted extensive debate among physicists, leading to various proposals and theories aimed at reconciling these disparate views. One prominent resolution includes the idea that information is not lost, but rather encoded on the event horizon itself, a concept that has given rise to the holographic principle. This principle suggests that all the data contained within a volume of space can be represented as a two-dimensional information structure at the boundary of that region, thereby preserving the information even when it appears that it has been lost. The implications of resolving the black hole information paradox extend beyond just understanding black holes. If information can never truly be lost, then the nature of reality might encompass more than our observable universe. Some theories suggest that resolving the paradox could involve multiverse scenarios. In these models, information that is lost in one universe could manifest in another universe, implying a connection between different realms of existence. Thus, when we contemplate the fate of information within a black hole, we might also be considering pathways to alternate realities or distinct universes where different physical laws apply. As researchers strive to untangle these intricate connections, the study of the black hole information paradox continues to fuel excitement in cosmology. Conversations around this topic not only challenge our understanding of black holes and the fundamental laws of physics, but also tantalize our imaginations regarding the nature of the multiverse and the possibilities it presents. The resolution of this paradox could very well redefine our concepts of reality, existence, and the interconnectedness of all things within the cosmos. Hawking radiation is a groundbreaking concept proposed by physicist Stephen Hawking in the mid-1970s, positing that black holes are not entirely black, but emit radiation due to quantum effects near the event horizon. This phenomenon arises from the interplay of particle-antiparticle pairs that spontaneously form and annihilate in the vacuum of space. When such a pair forms near a black hole, one particle might fall into the black hole while the other escapes, resulting in the gradual loss of mass from the black hole over time. Consequently, this radiation suggests that black holes can evaporate, potentially leading to their eventual annihilation. The implications of Hawking radiation are profound, challenging the traditional view of black holes as eternal, unchanging entities. If black holes can radiate energy and eventually disappear, it raises critical questions about what happens to the information stored within them. This directly ties into the black hole information paradox. If a black hole completely evaporates and information is lost, it contradicts the fundamental principles of quantum mechanics. Therefore, understanding Hawking radiation is crucial in developing a coherent framework that reconciles quantum mechanics with general relativity. Furthermore, Hawking radiation fuels speculative theories about the nature of the universe and its structure. If black holes can emit radiation and lose mass, could this process also lead to the creation of new universes? Some theories propose that the energy emitted as Hawking radiation could seed the formation of new cosmic structures or even isolated regions of spacetime that embody different physical laws, thereby hinting at the existence of a multiverse. In this view, black holes might act as both destroyers and creators, facilitating connections between diverse realms of reality. As scientists continue to explore the implications of Hawking radiation, the pursuit of a unified understanding of quantum physics and gravity remains a tantalizing challenge. Each insight gained from studying black holes will not only refine our comprehension of these mysterious objects, but also illuminate the potential pathways connecting our universe to others, shaping how we perceive the cosmos and our place within it. The fuzzball theory presents a fascinating alternative perspective on black holes, diverging from traditional views by proposing that black holes are not infinitely dense points of singularity, but rather complex, stringy structures. Emerging from string theory, which suggests that fundamental particles are made up of one-dimensional strings rather than points, the fuzzball framework describes black holes as a tangle of these strings. According to this model, what we perceive as a black hole is actually a collection of strings in a highly excited state, spread out over a vast region of space, rather than concentrated at a singular point. One of the compelling features of the fuzzball theory is its potential resolution of the black hole information paradox. Unlike conventional black holes that seemingly swallow information irretrievably, fuzzballs retain this information encoded within their complex string architecture. Therefore, the information about what falls into a fuzzball is not lost. Rather, it is preserved in the structure and dynamics of the fuzzball itself. This property aligns more closely with the principles of quantum mechanics, suggesting a more harmonious relationship between gravity and quantum theory. The implications of the fuzzball theory extend beyond the characteristics of black holes and into the realm of other universes. If black holes can be understood as fuzzballs, then it raises intriguing possibilities about their connections to other regions of spacetime or even entirely different universes. The stringy nature of fuzzballs might offer pathways or portals where different properties of spacetime can emerge, hinting at the existence of a multiverse where black holes serve as gateways to alternate realities with distinct physical laws or features. By expanding our understanding of black holes through the fuzzball framework, researchers may uncover new dimensions of cosmic architecture. The interplay between strings, gravity, and the information encoded in black holes holds the potential to address fundamental questions about the universe while shedding light on the tantalizing prospect of multiple universes coexisting alongside our own. As the exploration of fuzzballs continues, it invites not only a re-evaluation of black hole physics, but also a broader contemplation of the structure of reality itself. Primordial black holes, which are thought to have formed in the first moments after the Big Bang, offer a unique window into the conditions of the early universe. Unlike stellar black holes that originate from the collapse of massive stars, primordial black holes are believed to have emerged directly from density fluctuations in the hot, dense matter of the universe shortly after its inception. Studying these enigmatic objects can provide valuable insights into the universe's infancy, potentially shedding light on its formation and evolution during a time when conventional observations are challenging. One significant aspect of primordial black holes is their potential mass range. They could vary from very small, with masses less than that of an asteroid, to much larger ones, comparable to stellar black holes. The existence of smaller primordial black holes in particular raises intriguing questions related to dark matter. Some theories propose that if such black holes exist in sufficient quantity, they could contribute to the elusive dark matter that makes up a substantial portion of the universe's mass. Investigating their properties could therefore also enhance our understanding of the dark universe and its components. Furthermore, primordial black holes may offer clues about other realities or different regions of the universe. If certain mass ranges were associated with multiple formation processes or different physical conditions, the formation and characteristics of primordial black holes could hint at the multiverse concept, where our universe is just one of many with distinct physical principles. Researchers are exploring how primordial black holes might connect to different cosmic structures, perhaps acting as gateways to alternate regions of spacetime with unique properties. The study of primordial black holes intersects with the exploration of cosmic inflation, which posits that the universe underwent rapid expansion shortly after the Big Bang. Understanding how density fluctuations led to the genesis of these black holes may inform our broader theories on inflation and the formation of large-scale structures. As scientists continue to probe the enigmatic nature of primordial black holes, they not only enrich our knowledge of the early universe, but also enhance the discussion surrounding the existence of multiple realities, pushing the boundaries of our understanding of the cosmos. The simulation hypothesis posits that our reality, including the physical universe and everything within it, might be an artificial simulation, akin to a highly advanced computer program. This intriguing idea suggests that a sufficiently advanced civilization could create realistic simulations of their predecessors or entirely different worlds, leading to the possibility that we are currently living in one of these simulations. This concept has gained traction in popular culture and philosophical discourse, particularly in light of rapid advancements in technology and virtual reality experiences. One of the key arguments supporting the simulation hypothesis is based on the idea of probability. If it is feasible for advanced civilizations to create numerous simulations, then the number of simulated realities could far outnumber the original base reality. This suggests that beings within these simulations would greatly outnumber those in the original universe. Consequently, the likelihood that we are in the original reality becomes increasingly diminished, leading to the conclusion that we might indeed be part of a simulation. This hypothesis can also be linked to the framework of multiple universes. If our universe is just one of many simulations created by advanced beings, it implies a vast multiverse landscape where countless variations of realities exist. Each simulation could run distinct physical laws, cultural histories, or even evolutionary paths, resulting in a plethora of possible universes that diverge from our own. In this context, the term multiverse expands beyond the traditional interpretations in cosmology where multiple universes arise from different cosmological events, to include those generated through intelligent design. Exploring the simulation hypothesis encourages us to rethink fundamental questions about existence, consciousness, and reality. If our understanding of physics and the universe is merely a subset of a more profound simulation, it raises questions about the underlying purpose of these simulated realities and the nature of the beings that create them. As scientists, philosophers, and technologists delve into this captivating subject, the simulation hypothesis serves as a bridge between advanced technology, theoretical physics, and the contemplation of our place in the broader multiverse, illustrating how interconnected these concepts can be. The concept that our universe might be a simulation within a larger reality invites us to consider the possibilities of existence beyond our immediate perception. If we are living in a simulation, it implies that there exists a base reality, a more fundamental level of existence created or operated by advanced intelligences potentially beyond our understanding. This idea posits that everything we perceive, from the laws of physics to our very consciousness, may be the product of a meticulously crafted program designed to replicate or study a certain aspect of reality. One of the intriguing aspects of this notion is the idea that interconnected layers exist, where each layer may represent a different simulation or level of reality. The advanced civilization capable of creating such simulations could leverage vast computational resources, creating environments where every detail, from subatomic interactions to cosmic evolution, is programmed. As technology progresses, our own advances in virtual reality and artificial intelligence illustrate the plausibility of this concept, where increasingly sophisticated simulations become indistinguishable from real experiences for their inhabitants. In this framework, the universe we experience could be a very sophisticated simulation meant for various purposes, such as exploration, experimentation, entertainment, or even education. The inhabitants of this simulated universe, including all conscious beings, would be unaware of their existence within a larger framework, potentially leading to questions about free will, consciousness, and the fundamental nature of existence itself. If we are indeed living in this simulated reality, it raises profound questions about the Creator's intentions and the parameters set forth for our simulated world. Moreover, multiple simulations could coexist within this broader reality, leading to an array of distinct experiences and physical laws. Each simulation might be designed with different rules, offering a rich tapestry of realities that encompasses not just our universe but countless others, each with its own unique characteristics. This lines up harmoniously with the concept of the multiverse, where diverse universes arise due to varying conditions or histories. Collectively, these considerations illustrate how viewing our universe as a simulation within a larger reality challenges our perceptions of existence and compels us to reflect upon the underlying nature of everything we observe. The possibility of simulated universes brings forth a plethora of philosophical and scientific implications that challenge our understanding of reality, existence, and consciousness. Philosophically, one prominent consideration is the nature of existence itself. If our universe is a simulation, it prompts deep questions about what constitutes real. Are experiences, emotions, and thoughts any less valid if they occur within a fabricated reality? This inquiry pushes the boundaries of traditional metaphysics and invites us to rethink the essence of reality. The simulation hypothesis also ignites profound discussions about free will and determinism. If our lives are governed by predetermined algorithms crafted by an external programmer, do we possess genuine agency in our decisions? Alternatively, if we have free will, how does that fit within the parameters of a simulation? This dilemma stirs debates on moral responsibility, as concepts of right and wrong may take on different meanings in a simulated context where outcomes can be manipulated or observed. From a scientific standpoint, if the simulation hypothesis holds true, it challenges the foundations of physics and cosmology. Theories that govern our understanding of the universe, including quantum mechanics and relativity, may be seen as mere rules within a broader, overarching simulation framework. Scientists would need to pursue new methodologies to study the underlying code or principles that govern this simulated environment. This could lead to the development of novel scientific paradigms that explore the intersections of technology, consciousness, and fundamental cosmic laws. Moreover, the existence of simulated universes raises questions about the nature of consciousness. If conscious experiences arise within a simulation, it invites speculation about the source of consciousness itself. Are simulated beings truly conscious, or are they sophisticated mimicries of conscious thought? This contemplation may challenge our assumptions about artificial intelligence and the potential for machines to possess consciousness, influencing the ongoing ethical discussions surrounding AI and robotics. As we grapple with the implications of simulated realities, the dialogue becomes interdisciplinary, merging philosophy, science, technology, and ethics. By exploring these themes, we forge a deeper understanding of our place in the cosmos, questioning the very nature of reality, existence, and what it means to be truly alive within a potentially simulated universe. Detecting whether our universe is a simulation presents a formidable challenge, but intriguing ideas have emerged in philosophical and scientific discussions. One compelling approach lies in searching for signs of computational limitations within the fabric of the universe. Advocates of the simulation hypothesis propose that, much like digital simulations, our universe might exhibit discontinuities or anomalies that suggest it is not a perfectly continuous reality. For instance, exploring physical phenomena that appear quantized, like the discrete values of energy levels in atoms, could hint at underlying pixels or resolution limits of the simulated cosmos. Another avenue of investigation could involve the search for inconsistencies or mathematical patterns that align more with programming or computational shortcuts than with natural processes. If our universe operates under specific rules that resemble coding principles, researchers might uncover evidence of such structures through precision measurements in particle physics or cosmology. For instance, inconsistencies in the behavior of fundamental particles or unexpected correlations in cosmic microwave background radiation could serve as signals pointing to a simulated nature. Furthermore, advancements in technology, particularly in quantum computing and artificial intelligence, may facilitate the exploration of whether we exist within a simulation. As we develop more sophisticated algorithms and simulations ourselves, scientists might draw parallels or notice limits to their own creations that mirror features in our universe. This could offer insights into how a more advanced civilization might construct a simulation, and consequently, how we might discern whether our own universe follows similar patterns. Lastly, philosophical and theoretical frameworks could provide pathways to detecting a simulated universe. Engaging with questions about consciousness and observation can lead to deeper discussions about the nature of reality. If consciousness plays a role in shaping what we observe, an idea supported by interpretations of quantum mechanics, it raises the potential that our perceptions could be influenced by the confines of a simulation. Thus, re-evaluating how we experience reality and questioning the nature of our observations may also contribute to the discourse on whether we inhabit a simulated existence. Overall, while the detection of a simulated universe may be elusive, the interdisciplinary exploration of these ideas, combining insights from physics, technology, and philosophy, can enrich our understanding of reality and inspire innovative research that may one day illuminate the nature of our existence. The prospect of creating simulated universes raises a myriad of ethical considerations that delve into the foundational principles of morality, responsibility, and the meaning of existence itself. One of the foremost concerns is the treatment of sentient beings within these simulated environments. If we were to create intelligent life within a simulation, we must grapple with the moral implications of their experiences and rights. Are these beings entitled to the same considerations as conscious beings in the real world? Would their suffering, joy, or autonomy matter if they were merely products of a simulation? These questions force us to confront the nature of consciousness and the responsibilities we hold towards entities resembling us. In addition, the potential for gamesmanship regarding power dynamics emerges as a critical ethical issue. Creating a simulated universe could lead to disparities in control and authority. Those who design and run the simulation might possess the power to shape realities to their whims, potentially leading to abuses of power. This scenario echoes ethical concerns in our world regarding societal structures, oppression, and exploitation. The responsibility of the creators would extend beyond mere design to encompass ethical stewardship of the simulated beings and the environments they inhabit. Furthermore, the implications of simulating various scenarios, cultures, or societal structures present ethical dilemmas related to experimentation and observation. If a creator were to run scenarios that involve painful or traumatic experiences for the inhabitants, what moral justification could be offered for such actions? This becomes increasingly complex when considering the potential for suffering within simulations. Would it be ethically permissible to simulate historical atrocities or societal collapses as a means of study or entertainment? Such activities could desensitize creators and observers to real-world issues, luring them into a complacency regarding actual ethical considerations in life. Finally, the distinction between creator and creation raises philosophical questions about identity and existence. Boiling down the nature of reality into a simulated construct blurs the lines between creator and beings made from their design. Are the creators to be viewed as gods? And if so, what ethical guidelines must they adhere to? These reflections urge deeper self-examination and encourage us to establish ethical frameworks that guide our conduct if we were to gain the power and ability to create meaningful simulated worlds. Through this deliberation, our approach to simulations must be rooted in responsibility, compassion, and respect for consciousness, echoing the ethical principles that should govern our interactions in the actual world. String theory fundamentally reshapes our understanding of the universe by positing that the smallest building blocks of matter are not point-like particles, but rather one-dimensional objects known as strings. These strings can vibrate at different frequencies, and the various modes of vibration correspond to different particles, effectively unifying the forces and constituents of the universe. One of the most captivating aspects of string theory is its proposal of extra dimensions beyond the four we commonly experience: 3 dimensions of space and 1 of time. In string theory, for mathematical consistency and to accommodate all the vibrational patterns that strings can exhibit, additional spatial dimensions are required. While we are familiar with the 3 dimensions of space, length, breadth, and height, string theory suggests that there may be 6 or 7 more dimensions that are compactified or curled up in such a way that they remain hidden from direct observation. These additional dimensions could be as small as a fraction of the size of subatomic particles, making them extremely difficult to detect with current technology. The concept of compactified dimensions offers intriguing implications for the fundamental forces in our universe. For instance, how these extra dimensions are shaped and configured could influence the types of particles that emerge from string vibrations and determine the strength and behaviors of fundamental forces, such as gravity and electromagnetism. Different configurations of these extra dimensions might give rise to various physical phenomena, potentially explaining some of the observed inconsistencies in particle physics and cosmological observations. Moreover, the existence of these additional dimensions points to a richer and more complex cosmos. If indeed there are more dimensions, they may play roles that affect other theoretical constructs, such as black holes and the fabric of space-time itself. In some advanced interpretations of string theory, the dynamics of these hidden dimensions could shed light on cosmological questions, including the nature of dark matter and dark energy. As physicists continue to explore the ramifications of string theory and its extra dimensions, the prospect of a multidimensional universe offers not only deeper understanding of the fundamental aspects of reality, but also exciting pathways toward unifying the various forces of nature. These ideas open up new avenues for research, inviting a re-evaluation of everything we think we know about the universe and challenging our perceptions of what reality encompasses. Kaluza-Klein theory is a groundbreaking theoretical framework that combines the principles of general relativity with electromagnetism by introducing extra dimensions beyond the familiar three spatial dimensions and one of time. Developed in the early 20th century by mathematician Theodor Kaluza and later refined by physicist Oscar Klein, this theory originally aimed to unify gravity and electromagnetism in a coherent manner. The essence of Kaluza-Klein theory lies in the idea that by incorporating a fifth dimension, the complexities of electromagnetism could be mathematically represented as a geometric property of spacetime. In the Kaluza-Klein formulation, the fifth dimension is compactified, meaning it is curled up into a small circle and is therefore not directly observable in our everyday experience. This compactification allows for the existence of additional physical phenomena without disrupting the four-dimensional fabric of spacetime we perceive. The extra dimension fundamentally alters the equations of motion for particles, leading to the emergence of electromagnetic interactions as a natural extension of gravitational theory. The implications of Kaluza-Klein theory extend into the realm of higher dimensional physics and the consideration of multiple universes. By introducing the concept that our universe functions within a higher dimensional framework, it naturally lends itself to ideas about parallel or alternate universes. In certain versions of Kaluza-Klein theory, different compactification schemes could result in varying physical laws. This may imply the existence of multiple universes, each characterized by different properties, strengths of forces, or types of particles, shaped by the geometric structure of these additional dimensions. Moreover, the additional dimensions proposed by Kaluza-Klein theory could influence the way we understand fundamental forces. In the broader context of string theory, which also incorporates higher dimensions, these extra dimensions serve as vital components that help explain previously unexplainable properties of particles and forces. This interconnectedness not only emphasizes the importance of extra dimensions in modern physics, but also compels researchers to contemplate cosmological scenarios where diverse universes arise from different configurations of these dimensions. Overall, Kaluza-Klein theory represents a significant early attempt to unify gravity and other fundamental forces through higher dimensions, paving the way for further exploration into the nature of reality, the potential existence of multiple universes, and the relationships between the underlying structures of our cosmos. As physicists continue to investigate these ideas, Kaluza-Klein theory remains a crucial stepping stone in the pursuit of a deeper understanding of the universe's complexities. The idea of objects or beings existing in higher dimensions opens captivating avenues for understanding reality beyond our conventional experiences. In our daily lives, we perceive a three-dimensional world characterized by length, width, and height, as well as one dimension of time. However, if additional spatial dimensions indeed exist, as suggested by theories like string theory and Kaluza-Klein theory, beings or entities occupying these dimensions would have fundamentally different experiences and perceptions of reality. Entities in higher dimensions could possess qualities that exceed our ability to comprehend. For example, while we can only move freely within three spatial dimensions, a being existing in a higher dimensional space could navigate in ways we would find impossible. They might have the ability to cross through objects or perceive spatial relationships that remain hidden to us. This concept often leads to the analogy of how a two-dimensional being would struggle to understand the full qualities of three-dimensional objects. For instance, a flat creature in a two-dimensional plane would only perceive the edge of a solid sphere as a circle, missing its volume and depth entirely. Similarly, beings in higher dimensions would experience the intricate structures and relationships of our universe in ways we cannot visualize. If higher dimensional beings interacted with our three-dimensional world, their perception could encompass multiple perspectives simultaneously. They might see our universe as a slice or projection of a more complex reality, able to observe all possible configurations of particles and forces. Their ability to access and manipulate a broader range of dimensions could grant them insights into the fabric of space-time itself that remain elusive to us. Such beings might also experience time differently, potentially perceiving it as a more dimensional construct rather than a linear progression, leading to radically different understandings of causality and existence. The implications of their existence challenge our notions of consciousness and the nature of life. If entities in higher dimensions interact with our universe, what form of consciousness would they possess? Would they be aware of their dimensionality, or would they experience their own reality in isolation? These contemplations intersect with philosophical questions about intelligence and existence, encouraging us to expand our understanding of what life and consciousness might mean in the context of a multiverse. As we theorize about higher dimensional beings, we venture into a realm that stretches the boundaries of imagination and science. Exploring these concepts does not merely serve academic curiosity. It enlivens our quest to unravel the complexities of the universe and our place within it, inviting ongoing dialogue and exploration about the very nature of reality itself. The quest for experimental evidence supporting the existence of higher dimensions is a complex and ongoing endeavor in theoretical physics. While direct evidence remains elusive, several experimental approaches and observations offer tantalizing hints that higher dimensions might play a role in our understanding of the universe. One prominent method involves particle physics, particularly at large particle accelerators such as the Large Hadron Collider. In the context of string theory and other higher dimensional frameworks, one expectation is the potential discovery of particles or interactions that arise only because of extra dimensions. For instance, if additional dimensions exist, they could affect the behavior of fundamental particles under extreme energy conditions, possibly leading to specific signatures in collision events. Researchers are particularly focused on looking for evidence of mini black holes or particles that would hint at the underlying structure of higher dimensions as they engage particles at unprecedented energy levels. Another approach employs gravitational waves, which are ripples in spacetime caused by massive astrophysical events like colliding black holes. Detection of these waves by observatories such as LIGO and Virgo opens up the possibility of studying gravitational interactions that could reveal deviations from our current understanding based on general relativity. Should unexpected patterns or anomalies be observed in gravitational wave signals, it could suggest that the influences of additional dimensions are at play. Cosmic observations also provide insights into the potential existence of higher dimensions. For instance, the nature of dark matter and dark energy, the unseen forces that appear to dominate the universe, could be influenced by extra dimensions. Certain models suggest that the interactions between ordinary matter and dark matter might be explained differently if additional dimensions were involved. As scientists probe the distribution and behavior of dark matter in galaxies, they strive to differentiate between standard physics and scenarios that include higher dimensional theories. Lastly, the study of cosmic inflation, the rapid expansion of the universe immediately after the Big Bang, raises questions about the underlying mechanisms that drove this phenomenon. Theories that incorporate higher dimensions might present alternative explanations for inflationary dynamics, potentially providing signals in the cosmic microwave background radiation. Such signals could act as indirect evidence for the existence of dimensions beyond the four we typically perceive. While solid experimental evidence for higher dimensions has yet to emerge, these research avenues reflect a growing interest in uncovering the mysteries of the universe. As technology improves and our understanding deepens, the search for the elusive signatures of higher dimensions will undoubtedly continue, advancing our efforts to comprehend the fuller scope of reality. The concept of higher dimensions offers fascinating insights into phenomena that challenge our understanding of the universe, particularly dark matter and dark energy. Traditionally, we perceive our reality through three spatial dimensions, but theories such as string theory propose the existence of additional dimensions that we cannot easily observe. These extra dimensions may provide alternatives to the conventional explanations for dark matter and dark energy by suggesting that the forces and particles we experience are only a fraction of a more intricate and layered reality. One intriguing idea is that dark matter could be linked to these higher dimensions in such a way that it interacts with our familiar three-dimensional world. Instead of being composed of unknown particles, dark matter might be a manifestation of gravitational effects from matter residing in another dimension. This would mean that the gravitational pull we associate with dark matter is a result of influences from these unseen realms. Such a framework could simplify our understanding of why galaxies rotate at such high speeds, as the gravitational effects from the additional dimensions could account for the discrepancies observed. Dark energy, responsible for the universe's accelerating expansion, might also be influenced by higher dimensional theories. If the universe has additional spatial dimensions, the energy that pushes the cosmos apart could emanate from interactions across these dimensions. Instead of being a mysterious force acting solely within our three-dimensional space, dark energy could be a natural result of the geometry and dynamics of a higher dimensional universe. This suggests a link between the expansion of the universe and the structure of space-time itself beyond our conventional understanding. Exploring these higher dimensions not only enriches our theories about dark matter and dark energy, but also opens doors to numerous potential discoveries. The interplay between these dimensions could reveal connections between forces that we currently regard as separate. As physicists continue to delve into the mysteries surrounding these phenomena, our conceptual framework of reality may expand, revealing a universe far more complex and interconnected than we ever imagined. Quantum entanglement introduces a captivating possibility regarding the connection between our universe and others. At its core, entanglement describes a phenomenon where two or more particles become interconnected in such a way that the state of one instantaneously affects the state of the other, regardless of the distance separating them. This peculiar behavior challenges the classical understanding of communication and locality, suggesting that information can be shared across vast distances in ways that defy our traditional concepts of space and time. In the context of multiple universes, often referred to in theories such as the multiverse, entanglement could serve as a bridge between these realities. If entangled particles originated from different universes, a change in one could have immediate repercussions for the other, regardless of the physical separation. This interconnectedness suggests that the boundary between universes may be more porous than previously thought, allowing for a shared reality that transcends the isolated conditions we perceive. Moreover, some physicists theorize that entangled states could exist beyond our own universe, implying that the quantum information might flow between multiple universes. For instance, each entangled state might represent connections not only within our universe, but also to others that exist alongside it in a grand multiverse framework. This introduces profound implications for our understanding of reality, where events in our universe could potentially influence or be influenced by occurrences in parallel worlds. The exploration of quantum entanglement and its implications serves as an exciting frontier in modern physics. As researchers continue to unravel the complexities of quantum mechanics, the implications for our understanding of the universe's structure and the possibility of existence beyond our own invite us to reconsider the nature of reality itself, proposing a universe that is richly interconnected. Quantum decoherence is a fundamental process that plays a crucial role in the transition from the strange behaviors of quantum mechanics to the classical world we experience daily. At the quantum level, particles can exist in superpositions, where they occupy multiple states simultaneously. However, when a quantum system interacts with its environment, this delicate state begins to break down. The result of this interaction is that the superposition of states vanishes, leading to a definitive outcome. This phenomenon helps to explain why we do not observe the bizarre behaviors predicted by quantum mechanics in larger, macroscopic objects. The relationship between quantum decoherence and the concept of parallel realities is particularly intriguing. Many interpretations of quantum mechanics suggest that every possible outcome of a quantum event occurs, resulting in the existence of multiple parallel realities or universes. In this framework, each interaction that leads to decoherence effectively separates these realities. When a quantum system undergoes decoherence, the different possible states evolve into distinct, non-interacting branches of reality. Thus, what might seem like a single universe is actually a vast tapestry of branching scenarios, with each branch representing a different outcome of every quantum event. Decoherence provides a critical mechanism for understanding how these parallel realities can coexist without interfering with one another. Once a quantum system becomes entangled with its environment and experiences decoherence, the outcomes become practically independent. This separation allows each reality to develop its own unique history, ensuring that the many possible worlds remain distinct from one another, even if they originated from the same quantum state. The result is a multiverse framework where the outcomes of quantum events lead to the birth of different realities. Furthermore, understanding quantum decoherence has profound implications for fields like quantum computing and information theory. It highlights the challenges of maintaining quantum coherence in systems designed to harness quantum properties for technological advancements. As researchers continue to study decoherence and its role in the quantum realm, the implications for our understanding of parallel realities and the structure of the universe deepen, bringing us closer to grasping the complex nature of existence itself. The many interacting worlds interpretation of quantum mechanics presents a fascinating perspective on parallel universes, expanding upon traditional interpretations within the realm of quantum mechanics. This interpretation diverges from others, such as the Copenhagen interpretation, by eliminating the need for wave function collapse whenever a measurement is made. Instead, it suggests that all possible outcomes of quantum events are realized in separate, yet interacting branches of existence. According to this interpretation, when a quantum event occurs, such as a particle's position being measured, rather than collapsing into a single state, the universe splits into multiple coexisting realities. Each of these realities corresponds to a different outcome of that quantum measurement. For instance, if a particle has a 50% chance of being in one state or another, the many interacting worlds interpretation posits that both outcomes occur in their distinct branches of the universe. However, these branches do not drift apart completely. They retain the potential for interaction through quantum entanglement. What makes the many interacting worlds interpretation particularly intriguing is the notion that these parallel worlds can affect one another. The interactions can lead to interference patterns similar to those observed in quantum systems. For example, the outcomes in one branch of reality can influence or inform the behavior of another. This interaction implies a complex web of interconnected universes, establishing a framework where our choices and actions resonate through a broader tapestry of existence. This interpretation of quantum mechanics adds a layer of richness to our understanding of reality, as it suggests that rather than experiencing a single linear timeline of events, we are part of a much larger interconnected multiverse. Each decision we make or chance we encounter unfolds pathways leading to multiple, simultaneously existing realities. This provides a captivating lens through which to view our existence, emphasizing how quantum mechanics may govern not only the microscopic world, but also the fabric of reality itself, intertwining our experiences with countless parallel histories. Experimental evidence supporting quantum effects at a cosmic scale highlights the remarkable interconnection between the microscopic realm of quantum mechanics and the vast universe. One of the most compelling examples comes from the phenomenon of cosmic microwave background radiation, which is regarded as the remnant light from the Big Bang. Tiny temperature fluctuations in this radiation, as measured by satellites like the Wilkinson Microwave Anisotropy Probe, suggest quantum fluctuations in the very early universe. These fluctuations set the initial conditions that led to the large-scale structures we observe today, such as galaxies and clusters of galaxies. Another significant piece of evidence comes from the study of large-scale entanglement and quantum coherence in cosmological contexts. Research exploring the behavior of light from distant sources has shown that quantum effects can persist over vast distances, challenging our understanding of separability in classical physics. Experiments involving pairs of entangled photons point toward the influence of quantum mechanics on cosmic scales, as these photons maintain their entangled state despite being separated by significant distances. In the realm of astrophysics, the study of supernovae and neutron stars has provided further insights into quantum effects at cosmic scales. These events create extreme conditions where quantum behaviors become pivotal. For example, The behavior of dense matter in neutron stars is governed by quantum mechanics, as they are composed primarily of neutrons organized in quantum states that cannot be described by classical means. Observations of pulsars, which are neutron stars emitting beams of radiation, also imply that quantum processes are at play in their rotation and electromagnetic emissions. Additionally, the quest to detect gravitational waves has led to experiments that simultaneously explore quantum mechanics and general relativity. The Laser Interferometer Gravitational Wave Observatory utilizes highly sensitive quantum technologies to measure gravitational waves produced by cosmic events like the collision of black holes. The precise nature of these measurements, reliant on quantum effects, bridges the gap between the quantum realm and the cosmic landscape, reinforcing the idea that quantum mechanics is not confined to the tiny scales of atoms and particles, but permeates the universe itself. This body of evidence inspires ongoing research into the fundamental connections between quantum physics and cosmology, revealing a universe that is more interconnected than we once believed. Harnessing quantum entanglement to communicate or interact with other universes is an intriguing concept that opens doors to possibilities far beyond our current technological capabilities. Entanglement allows pairs or groups of particles to become interconnected in such a way that the state of one particle directly influences the state of another, regardless of the distance separating them. This unique property raises questions about the potential for entangled particles to facilitate communication across different universes, particularly within frameworks that embrace the notion of a multiverse. One theoretical approach to utilizing quantum entanglement for inter-universal communication involves creating entangled pairs of particles across distinct branches of the multiverse. If we assume that these branches can interact through quantum processes, then changes made to one entangled particle could instantaneously affect its partner in another universe as well. This suggests a mechanism by which information could potentially be shared or exchanged across realities, although the practical aspects of such communication remain in the realm of speculation. Another avenue for exploration involves the concept of quantum teleportation. This process utilizes entanglement to transfer the quantum state of one particle to another without physically moving the particle itself. If we could establish a method for teleporting quantum states between universes, it might allow for the transference of information or even particles themselves. However, significant challenges remain, as this would require a sophisticated understanding of the connections between the quantum states of particles across universes and a means of maintaining the delicate entangled states over such vast separations. Furthermore, entangled particles could provide insights into the nature of parallel realities by examining how their states might differ or correlate. By measuring the outcomes of entangled particles in our universe, we could gather information about corresponding states in other universes. This experimental exploration could pave the way for understanding the physical laws that govern these realities and how they interconnect with our own. While the concept of using quantum entanglement to interact with or communicate across universes is deeply theoretical and fraught with challenges, it opens a fascinating window into the potential capabilities future technologies might one day achieve. As our understanding of quantum mechanics evolves, striving to comprehend the boundaries between universes may bring us closer to realizing the extraordinary implications of the interconnected multiverse. Cosmic voids are vast, empty spaces in the universe that contain very few galaxies or matter compared to denser regions. These voids can stretch for tens to hundreds of millions of light-years and make up a significant portion of the universe's large-scale structure. In contrast to the filaments and clusters where galaxies congregate, cosmic voids appear as the great emptiness, highlighting the intricate web-like distribution of matter throughout the cosmos. The study of cosmic voids has revealed that they are not mere absences of matter, but rather play a critical role in the evolution and behavior of the universe. These regions can affect the motion of galaxies and influence the distribution of dark matter through their gravitational effects. As galaxies move through the cosmos, they tend to cluster along the edges of these voids, creating boundaries that define their structure. By observing the properties and distributions of voids, astronomers gain insight into the overall dynamics of the universe and the processes that shaped it. The relationship between cosmic voids and regions beyond our observable universe is a subject of great intrigue. Since cosmic voids represent some of the largest structures in the cosmos, they may suggest that similar empty regions exist beyond the limits of what we can currently observe. The universe continues to expand, and light from distant regions may not yet have reached us, leaving the possibility of vast areas filled with voids or different structures beyond our observational horizon. Furthermore, some cosmological models propose that these voids could be tied to the fundamental dynamics of the multiverse, where multiple universes exist in diverse configurations. If our universe is just one of many, the principles governing the creation and arrangement of matter may operate differently in other realities, leading to different patterns of voids and structures. By studying the nature of cosmic voids within our universe, researchers can glean clues about the potential character of regions beyond our observable limits, offering a tantalizing glimpse into the underlying fabric of reality itself. Supervoids are enormous regions of space that are significantly less dense than average, often spanning hundreds of millions of light years and containing far fewer galaxies than typical cosmic regions. These vast, underpopulated areas stand in contrast to the denser cosmic structures such as galaxy clusters and superclusters. The existence of supervoids presents intriguing challenges to our understanding of cosmic structure formation, especially regarding how matter is distributed throughout the universe. One significant challenge posed by supervoids is their implication for the current models of the universe's evolution. Cosmological theories, particularly those related to the distribution of galaxies and dark matter, are based on the premise that matter is relatively uniformly distributed in the universe, leading to the sponge-like structure filled with filaments and voids. Supervoids, however, suggest that large regions of space can exist in relative emptiness, prompting scientists to reconsider how these vast voids formed without resulting in noticeable gravitational consequences on surrounding structures. Additionally, the presence of supervoids raises questions about the role of dark energy in cosmic evolution. Dark energy is believed to be responsible for the accelerated expansion of the universe, and supervoids might act as natural laboratories to study its effects. Observations of light from distant objects passing through supervoids have indicated the possibility of distortions in the cosmic microwave background and gravitational lensing effects, which can be used to explore the influence of dark energy on cosmic scales. Understanding how dark energy interacts with these supervoids can enrich our knowledge of the dynamics governing cosmic structure formation and expansion. Furthermore, the peculiarities of supervoids challenge our grasp of fundamental physics. For instance, some researchers have proposed that supervoids may be tied to the existence of large-scale inhomogeneities in the universe, or even hint at the existence of complex cosmic phenomena such as anomalies or exotic matter. These insights could provide fresh perspectives on the interplay between gravity, dark matter, and the fundamental forces shaping the universe. As studies of supervoids continue, they serve as a fascinating lens through which to refine our understanding of cosmic structure formation. Their investigation encourages scientists to delve deeper into the nature of voids, growth processes in the universe, and the underlying principles that govern the vast cosmic arena we inhabit. The cold spot in the cosmic microwave background radiation is a notable area that appears significantly cooler than the surrounding regions. It was discovered through measurements taken by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft, which analyzed the remnants of the Big Bang. This cold spot is unusual because it spans a substantial area of the sky, challenging the standard cosmological models that predict a more uniform temperature distribution across the cosmic microwave background. One intriguing aspect of the cold spot is its potential connection to the concept of other universes, or a multiverse theory. Some researchers postulate that the cold spot could be an imprint of a collision between our universe and another universe. According to this idea, if two universes were to collide, the interaction could create localized effects in the cosmic microwave background, resulting in temperature anomalies like the cold spot. This hypothesis suggests that we might be observing a remnant of a multiverse event, implying that our universe is not isolated, but potentially part of a broader fabric of realities. In addition to the multiverse theory, alternative explanations for the cold spot have also been proposed. Some scientists suggest it may be the result of large-scale cosmic phenomena, such as structures that form during the evolution of the universe, or it could arise from the gravitational influence of supervoids, which are vast, empty regions of space. Other theories even point to potential systematic errors in measurement or the effects of foreground emissions from our galaxy that could mask the true nature of this anomaly. While the cold spot remains a subject of intense study and discussion, it serves as a vivid reminder of the complexities inherent in cosmology. As researchers continue to investigate this intriguing phenomenon, its implications extend beyond our understanding of the cosmic microwave background, offering tantalizing possibilities about the existence of other universes and the interconnectedness of reality itself. Exploring the nature of the cold spot may play a vital role in uncovering profound truths about the universe's structure and its place within a larger cosmic landscape. Cosmic voids, with their vast empty expanses and lower-than-average densities, have captivated scientists by suggesting they might play a role in understanding deeper aspects of our universe, including the notion of other realities. These enormous, underpopulated regions could serve as windows or gateways to different realms, particularly when considered in the context of theories about the multiverse. One way cosmic voids might connect to other realities is through their unique gravitational effects. Due to their lower density, voids can warp the fabric of space-time differently than denser regions filled with galaxies. This warping might create pathways through which we could observe or even interact with parallel universes, depending on the complex interplay of gravity and quantum mechanics. If other universes exist with distinct properties, the gravitational influence of cosmic voids could hypothetically allow for the influence of their fields, possibly leading to observable effects in our universe. Moreover, the very nature of voids aligns with current theories about cosmic expansion and structure formation, which often predict the existence of other dimensions or universes. Some physicists propose that the vast emptiness of voids could provide evidence for the boundaries between our universe and others. In this scenario, voids might represent areas where the fabric of reality is less dense or configured differently, providing hints of other, perhaps more exotic realms that share an intricate connection to our own. Additionally, the study of voids may shed light on the fundamental structure of spacetime itself. If cosmic voids are accompanied by other dimensions or hidden realms, they could reveal insights into how matter organizes and evolves in the universe. Future discoveries in void research could open the door to theories of interdimensional interaction, inspiring exploration of ideas resembling quantum entanglement that bridge different realities. These scientific inquiries push the boundaries of our comprehension, inviting us to consider whether the empty spaces in the cosmos are merely voids or gateways to a broader multiverse that awaits discovery. The investigation of cosmic voids holds the potential for significant revelations about the universe and the possibility of alternate realities. By exploring these massive expanses of space, scientists hope to uncover connections that could expand our understanding of existence itself, propelling us toward new theories and possibilities that enrich our view of the cosmos and our place within it. A variety of observational techniques are employed to study cosmic voids and unravel their properties, enhancing our understanding of these fascinating structures within the universe. One of the primary methods relies on large-scale surveys of galaxies and their distribution across the sky. Surveys such as the Sloan Digital Sky Survey compile extensive data on galaxy positions and redshifts, enabling astronomers to map out large-scale structures. By analyzing the density of galaxies in different regions, researchers can identify voids and characterize their dimensions, shapes, and environments. Another significant technique involves gravitational lensing, which examines how the presence of mass, such as galaxies or dark matter, can distort the light from more distant objects. In void regions, where the gravitational influence is weaker, The effects of lensing can provide insights into the distribution of matter and dark energy. By studying how light is bent from sources behind cosmic voids, scientists can infer the distribution of unseen mass and assess the influence of the voids on surrounding structures, offering clues about the overall dynamics of the universe. Additionally, the cosmic microwave background radiation serves as a powerful tool for studying cosmic voids. Temperature fluctuations in the cosmic microwave background can reveal the influence of large-scale structures, including voids, on the early universe. Scientists analyze how the voids might have affected these temperature patterns, providing insight into their formation and evolution. This approach is particularly useful for understanding the relationship between voids and the cosmic web, as well as their role in the universe's expansion history. Moreover, simulations and computer models play an essential role in the study of cosmic voids. By simulating the evolution of the universe, researchers can predict how voids form and change over time under various cosmological parameters. By comparing these simulations with observational data, astronomers can refine their understanding of void characteristics and dynamics. These combined observational techniques not only enhance our knowledge of cosmic voids, but also improve the overall understanding of cosmic structure formation and the fundamental processes that govern the universe. The nature of time in regions beyond our observable universe is a deep and complex topic that challenges our current understanding of cosmology and fundamental physics. In our observable universe, time is usually considered to flow uniformly, shaped by the curvature and expansion dictated by general relativity. However, as we contemplate regions beyond what we can observe, various factors suggest that the concept of time may differ significantly. One intriguing possibility relates to the idea that time may not be uniform or absolute in distant regions. According to some theories, as one moves further from our observable limit, variations in the cosmic structure, including density and gravitational fields, could alter the flow of time. For instance, areas with different gravitational intensities can exhibit time dilation effects, where time moves more slowly in stronger gravitational fields. In regions beyond our observable universe, where we lack empirical data, it is plausible that entirely different mechanisms could be at play, resulting in varying experiences of time. Furthermore, concepts like cosmic inflation and multiverse theories introduce the notion that the fabric of space-time may not be entirely continuous. If our universe underwent rapid inflation, it could imply the existence of other, possibly disconnected regions of space-time, each with their own unique timelines. These regions might not be bound by the same temporal rules, raising profound questions about how events in those areas could unfold independently of our universe's timeline. Interestingly, quantum mechanics hints at the non-classical nature of time itself. In certain interpretations, such as those involving quantum entanglement or superposition, the rigid structure of time might dissolve, leading to scenarios where time behaves differently. If these principles extend to regions beyond our observable universe, it could suggest a reality where temporal sequences are more fluid or less predictable. Exploring the potential variations of time in distant regions not only expands our understanding of cosmological principles, but also pushes the boundaries of theoretical physics. As researchers continue to pursue these questions, they may uncover remarkable insights that redefine our comprehension of time, challenging our assumptions about its universality and presenting new dimensions of reality. Causal disconnection refers to the phenomenon where certain regions of space become isolated from one another, preventing any form of communication or interaction between them. This concept arises from the framework of relativity, where the speed of light serves as a fundamental limit on how quickly information and influence can travel through the universe. When two areas become causally disconnected, events occurring in one region cannot affect or be observed in the other, as any signals or light emitted would take longer than the age of the universe to bridge the gap. In relation to the boundaries of our observable universe, causal disconnection plays a critical role in shaping our understanding of cosmological limits. The observable universe is defined by a spherical region centered around us extending outward to the distance that light has traveled since the Big Bang, approximately 13.8 billion years ago. Beyond this boundary lies regions of space that we can never observe or interact with because the light or signals emitted from those areas has not yet reached us. These regions are causally disconnected from our own observable universe. As the universe expands, it is possible for some galaxies or structures to move beyond our observable limit at a speed greater than that of light due to the expansion of space itself. This means that while these objects once were part of the universe we could see, they can become hidden from us as the fabric of space stretches. Consequently, the cosmos can contain vast swathes of reality that remain forever unreachable and unobservable from our vantage point. The idea of causal disconnection also leads to fascinating implications about the nature of reality itself. It implies that there could be regions of the universe with entirely different physical contexts, possibilities or events occurring that we will never be able to know about or affect. This disconnection raises intriguing questions about the overall structure of the universe and the potential existence of other connected realities beyond our observational limits, further deepening the mysteries of the cosmos and our place within it. Closed time-like curves, or CTCs, are fascinating concepts arising from the equations of general relativity, which allow for paths through spacetime that loop back on themselves, theoretically enabling an object or observer to return to an earlier point in time. While our own universe appears to operate under the conventional flow of time, the existence of closed time-like curves invites speculation about how they might manifest in other universes or regions of space. One theoretical framework where closed time-like curves could exist involves the concept of wormholes. Wormholes are hypothetical passages through space-time that could connect distant points in both space and time. If a wormhole were traversable, it might allow for travel back to an earlier moment in time, creating a closed time-like curve in the process. While no empirical evidence for such structures exists, the mathematics of general relativity supports their theoretical possibility, suggesting that regions of space-time could be configured in ways that permit CTCs. In addition to wormholes, certain cosmological models, such as those involving rotating black holes, known as Kerr black holes, might also give rise to closed time-like curves. The unique space-time geometry around rotating black holes could theoretically create regions where time loops occur, enabling paths back to prior moments in time. This suggests that in regions of high gravitational influence and intense curvature, such as near a black hole, the nature of time may behave differently, potentially allowing temporal loops to form. Exploring the existence of closed time-like curves also leads to intriguing implications regarding parallel universes or multiverse scenarios. If multiple universes coexist with distinct physical laws or configurations, it is conceivable that some of these universes could support the formation of CTCs while others do not. Such a diversity in cosmic structures could produce entirely different temporal landscapes, challenging our understanding of causality and the linear progression of time. While the idea of closed time-like curves raises profound questions about time travel and the nature of reality, it also encourages deeper inquiry into the fabric of space-time itself. As scientists probe the boundaries of theoretical physics, the search for evidence supporting or refuting these ideas could ultimately expand our understanding of the universe and its potential complexities, enriching our perspective on existence beyond conventional temporal limits. The concept of baby universes refers to hypothetical miniature universes that may form as separate, distinct regions within a larger cosmic framework. The idea suggests that these smaller universes could branch off from our own due to certain cosmic processes, leading to the genesis of entirely new realms of space-time with their own unique physical properties and laws. This notion has captivated cosmologists, particularly in the context of theories involving inflation, black holes, and the multiverse. One way baby universes might form is during cosmic inflation, a rapid expansion of space that occurred shortly after the Big Bang. During this phase, fluctuations in energy density could lead to the creation of localized regions where inflation continues, effectively giving rise to a baby universe that detaches from the parent universe. These nascent universes could then expand and evolve independently, developing their own distinct characteristics over time, while also being a product of the original universe's physical laws. Black holes also offer a tantalizing avenue for the formation of baby universes. Some theoretical models suggest that within the singularity of a black hole, space-time could behave so differently that it creates conditions for an entirely new universe to emerge. If a baby universe were to form in this manner, it might remain entirely disconnected from our observable universe, leading to realms where the physics could dramatically differ. This separation could explain why we see black holes as regions of no return. The material drawn into them could be funneled into a newly formed universe. The concept of baby universes also ties into multiverse theories, which propose that our universe is just one of an infinite number of universes. In this framework, baby universes might be numerous, potentially forming constantly as a natural consequence of cosmic evolution. Each of these universes could bear the imprint of their parent universe, while developing unique traits that allow for diverse forms of existence, physical laws, and even varying constants of nature. While the idea of baby universes remains largely theoretical, contemplating their existence challenges our understanding of reality and invites further exploration of the cosmos. As scientists continue to investigate the fundamental principles governing the universe, the mechanisms behind baby universe formation could provide profound insights into the interconnectedness of existence and the possibilities lying beyond our own universe's observable limits. The arrow of time refers to the observable direction in which time seems to flow, typically from the past to the future. This concept is intrinsically linked to the second law of thermodynamics, which states that in an isolated system, entropy tends to increase, leading to a progression towards disorder. In the context of multiple universes, the arrow of time raises intriguing questions about how time evolves and behaves across potentially disparate realities. In a multiverse scenario, each universe may have its own distinct arrow of time, influenced by specific initial conditions, physical constants, and the distribution of matter and energy. This means that while our universe exhibits a straightforward arrow of time due to the increasing entropy associated with its expansion and interactions, other universes may experience entirely different temporal flows depending on their unique structures. Some universes could have scenarios where the arrow of time does not behave as it does in our universe, potentially flowing backwards or displaying complex behaviors influenced by their own internal dynamics. The evolution of multiple universes may also be intrinsically related to cosmic events and phenomena. For example, universes that undergo different types of cosmological inflation or collapse could give rise to various arrows of time based on their thermal histories and entropy changes. As universes evolve, their individual arrows of time may dictate how structures form, how galaxies and stars develop, and how life, if it exists, evolves within those frameworks. Furthermore, the concept of the arrow of time in the context of quantum mechanics ties into this discussion. In certain interpretations, such as the many worlds interpretation, the branching of realities might be influenced by quantum events and superpositions. Each branch where a measurement occurs could exhibit its own arrow of time, diverging from the others based on the outcomes of quantum interactions. This highlights a potential linking of time's directionality in both macroscopic and microscopic realms across different universes. Overall, the relationship between the arrow of time and the structure and evolution of multiple universes invites profound contemplation about the fundamental nature of reality. As researchers investigate these concepts, they delve into some of the most complex questions regarding time itself, exploring how it shapes our understanding of existence and the diverse possibilities that may lie beyond our own universe. Dark flow is a phenomenon observed in cosmology that refers to the unexpected, large-scale motion of galaxy clusters in a specific direction. This peculiar movement was first identified through measurements of the cosmic microwave background radiation, particularly by studying the motion of clusters away from the average distribution predicted by the standard model of cosmology. The observed motion suggests that these clusters are not merely expanding uniformly, but are instead being influenced by some gravitational pulls from unseen structures beyond our observable universe. One potential explanation for dark flow points to the existence of massive structures that lie beyond the boundaries of what we can observe. These structures could include vast galaxy clusters or superclusters that emit gravitational forces strong enough to impact the motion of nearby galaxy clusters. Since these regions are out of the observable reach, they remain hidden from direct observation, making the gravitational influence we detect through dark flow a critical clue pointing toward their existence. The implications of dark flow extend into the realm of multiverse theory as well. If dark flow indicates that there are structures beyond our observable universe, it raises profound questions about the arrangement and nature of these regions. Some theories suggest that these unseen influences might even connect to other universes, suggesting a shared cosmic environment with different characteristics, densities, or principles of physics. Such interactions could potentially explain the large-scale motions observed and lead to greater insights about the overall topology of the cosmos. Studying dark flow presents both exciting possibilities and significant challenges for astronomers. It underscores the need for deeper investigations into the large-scale structure of the universe and the gravitational dynamics governing galaxy clusters. As we continue to refine our methods and gather more data, dark flow may unveil crucial information about the cosmic landscape, possibly leading to a better understanding of the nature of the universe and the enigmatic structures that lie beyond our correlating horizons. Large-scale structures like galaxy filaments and walls play a crucial role in our understanding of the universe, especially concerning the limits of our observable universe. These structures form a vast, intricate cosmic web composed of matter, including galaxies and dark matter, interconnected by gravity. They arise from the gravitational attraction of matter over billions of years, leading to regions of higher density where galaxies cluster together while vast voids remain largely empty. Understanding how these structures relate to the boundaries of our observable universe provides insight into the overall architecture and evolution of the cosmos. Within our observable universe, galaxy filaments are the threads of this cosmic web, creating vast, elongated structures that can stretch for hundreds of millions of light years. These filaments connect clusters of galaxies, forming a network that outlines the distribution of cosmic matter. Walls, on the other hand, are more extensive, flat structures representing the densest regions within the cosmic web, where clusters of galaxies are agglomerated along their surfaces. As we study these large-scale structures, we uncover crucial details about the formation of galaxies and the distribution of dark matter, which drives the development of the universe. The distribution of these structures also presents a unique relationship with the limits of our observable universe. As we look farther into space, we observe regions that are less influenced by large-scale structures due to light travel time constraints. The observable universe is limited to what we can detect within a spherical volume that has expanded outward since the Big Bang, which means that certain large-scale structures may exist beyond our observational reach. This limitation creates a scenario where only parts of the cosmic web are visible, leaving other potential filaments and walls inaccessible for direct observation. The understanding of large-scale structures can also help theorize about the broader universe and the regions that extend beyond our observable limits. The patterns observed within our universe can provide clues about the universe's overall topology and how structures might organize in regions we cannot currently see. This relationship encourages speculation about the existence of similar or entirely different structures in the unobservable universe, leading to intriguing possibilities regarding the nature of reality and the interconnectedness of cosmic bodies throughout the cosmos. As our observational techniques advance, we may expand our view of large-scale structures, bringing us closer to understanding the full extent of the universe and what lies beyond the limits of our sight. The axis of evil in cosmology refers to an unexpected alignment observed in the cosmic microwave background radiation data. Initially detected by scientists analyzing annular structures in the cosmic microwave background, this alignment suggests that certain large-scale features in the universe have a directional bias. Specifically, this axis appears to point towards a region in the sky, raising questions about the isotropy of the cosmos, which is the principle that the universe should look the same in all directions when averaged over large scales. This discovery has significant implications for our understanding of cosmic isotropy, as it challenges the standard cosmological model that posits a homogeneous and isotropic universe. If the universe is truly isotropic, cosmic microwave background radiation should display consistent properties regardless of the direction in which we observe. However, the alignment of temperature fluctuations and the orientation of large-scale structures in the axis of evil hints at an underlying asymmetry that contradicts the predictions of the isotropic model. There are various explanations proposed to account for this phenomenon. Some scientists speculate that the axis of evil could result from statistical anomalies or foreground contamination within our own galaxy affecting the observations. Alternatively, it may imply that there are cosmic structures or influences yet to be discovered, including potential interactions with regions beyond our observable universe that influence these measurements. If the axis of evil is indeed a genuine feature of the universe, it could suggest that our understanding of cosmic expansion, structure formation, and the overall nature of the cosmos needs re-evaluation. The implications could reach far into the realms of fundamental physics, influencing our grasp of dark energy and other cosmological components, or even hinting at the multiverse theory in which local anisotropies could arise from interactions with other universes. Investigating the axis of evil continues to stimulate scientific dialogue and exploration. As researchers gather more data and improve measurement techniques, we may gain deeper insights that either confirm or challenge existing cosmological models. Ultimately, these inquiries could lead to breakthroughs in our understanding of the universe's structure and dynamics, as well as the fundamental principles governing its behavior. Gravitational waves are ripples in the fabric of space-time that are produced by some of the most violent and energetic processes in the universe, such as the collision of black holes or neutron stars. Their detection, primarily by observatories like the Laser Interferometer Gravitational Wave Observatory, has opened a new window into the cosmos, allowing scientists to gather information that goes beyond what can be observed through conventional electromagnetic signals like light. One key way gravitational waves could provide insights into regions beyond our observable universe is through their ability to reveal information about cosmic events that occur at vast distances. Because gravitational waves travel at the speed of light and are less affected by intervening matter than electromagnetic radiation, they can carry information from regions that are otherwise obscured or unreachable. For instance, merging black holes or neutron stars that generate gravitational waves may occur in areas of space that are beyond our observational reach, allowing us to indirectly study events occurring outside our observable universe. Interestingly, the properties of the gravitational waves we detect can also offer clues about the environments from which they originate. Analyzing the frequency, amplitude, and waveforms of these signals can inform researchers about the mass and energy dynamics of the colliding bodies. If we were to detect gravitational waves from events that may be tied to the early universe, such as primordial black holes or phenomena from the time of inflation, it would deepen our understanding of the conditions that shape the cosmos and provide insights into regions that have since moved beyond the limits of what we can see. Moreover, gravitational waves may illuminate the nature and behavior of dark matter and dark energy, components that influence the universe's large-scale structure but remain elusive under conventional observation. By studying how gravitational waves interact with these entities, researchers could gain a better understanding of their influence across vast distances, potentially bridging knowledge gaps about cosmic regions outside our reach. As detection techniques improve and the science of gravitational wave astronomy progresses, the potential for discovering new phenomena and gathering information about the unseen corners of the universe is substantial. This could revolutionize our understanding of cosmic history and the complexities that lie beyond the boundaries of our observable universe, revealing a landscape rich with potential discoveries and shifting our perceptions of existence in the cosmos. Dark matter plays a crucial and complex role in the structure and dynamics of our universe, and its properties may also illuminate connections to other universes. Comprising about 27% of the universe's total mass energy content, dark matter does not interact with electromagnetic forces like ordinary matter, making it invisible and detectable only through its gravitational effects. This elusive nature means it may not only influence the behavior and formation of structures within our universe, but also hint at the existence of unseen realities beyond our observable realm. One possibility is that dark matter could serve as a bridge between universes, particularly in the context of multiverse theories. If there are multiple universes with varying physical laws or dimensions, dark matter may have different manifestations or properties in those realities. For instance, if certain forms of dark matter were to interact with the fabric of space-time in unique ways, they might create pathways or distortions that could connect our universe with others. Such interactions could lead to gravitational influences that leave detectable traces within our universe, even if the other universes remain inaccessible. Additionally, the dynamics of dark matter could provide insights into how universes might evolve. Since dark matter affects the formation of galaxies and large-scale structures, understanding its behavior may reveal how similar structures could arise in other universes under different physical laws. For example, if the composition or properties of dark matter varied, this could lead to divergent evolutionary pathways for cosmic structures, not just in our universe, but in neighboring ones as well. The nature of dark matter also suggests that its study could yield insights into fundamental physics, potentially bridging gaps between our understanding of quantum mechanics and general relativity. If dark matter is found to involve quantum effects, this could point toward a more intricate web of interactions that might extend beyond our universe. The potential existence of hidden dimensions or alternate realms, as suggested by some models of dark matter particle physics, may open avenues to theorize about connections between the universes. Exploring the implications of dark matter not only helps unravel the mysteries of our universe, but also inspires inquiries into the larger structure of reality itself. As scientists continue to investigate dark matter's properties and roles, we are continually challenged to consider the boundaries of existence and the potential for interactions with other universes, ultimately expanding our understanding of the comprehensive cosmic landscape we inhabit. The study of quantum gravity aims to unite the principles of quantum mechanics and general relativity, addressing one of the most significant challenges in modern theoretical physics. By understanding how gravity behaves at the quantum level, researchers hope to uncover insights into the fundamental fabric of reality, particularly regarding what might exist beyond our universe. One crucial aspect of quantum gravity is its potential to reveal the nature of space-time itself. Many theoretical approaches, such as string theory and loop quantum gravity, suggest that space-time is not a continuous entity, but rather is constructed from discrete elements or fundamental strings. This perspective allows for the possibility that our universe is a part of a larger, more complex structure, where the geometry of space-time could have different properties in regions beyond our observable limits. Such frameworks may lead to a better understanding of how other dimensions or universes could interact with our own, offering glimpses into the potential complexities that lie beyond the familiar fabric of our reality. Additionally, quantum gravity may provide insights into scenarios involving black holes and singularities. When matter collapses into black holes, the conventional laws of physics break down, leading to conditions that challenge our understanding of time and space. Exploring these extreme environments could reveal information about the informational structure of black holes, which may serve as conduits or portals linking to other regions of the universe or even alternate universes. This could pave the way for theories that propose that information is never truly lost, suggesting that connections between universes could exist through gravitational interactions and transitions. Moreover, Advancements in understanding quantum gravity could lead to new paradigms in cosmology, particularly in explaining cosmic phenomena such as inflation or the Big Bang itself. If a deeper theory of quantum gravity can accurately describe the dynamic processes of the early universe, it may indicate how regions of space-time emerged, potentially hinting at the existence of other universes created within an overarching multiverse framework. This could reshape our understanding of the universe's expansion and evolution, revealing influences from dimensions or realities beyond our perception. Thus, the study of quantum gravity stands to significantly enhance our grasp of the foundational aspects of the cosmos, bridging gaps between observed phenomena and theoretical frameworks. As researchers explore the implications of quantum gravity, they may increasingly uncover knowledge that not only enlightens us about the universe we inhabit, but also expands our understanding of what exists beyond its observable boundaries, pushing the frontiers of human knowledge into uncharted territories. The concept of a multiverse landscape arises primarily from string theory and cosmological considerations, proposing that our universe is just one of many, each with its own unique physical laws and constants. This landscape is often visualized as a vast collection of possible vacuum states, where different regions of the landscape correspond to different configurations of fundamental parameters. Each configuration could give rise to a unique universe with distinct properties, from variations in the forces of nature to differing dimensional structures. To study the multiverse landscape, researchers utilize a variety of theoretical and computational approaches. One significant method involves analyzing string theory's mathematical formulations, which inherently predict a vast number of solutions corresponding to different vacuum states. By examining these solutions, physicists can identify potential physical characteristics and their implications, allowing exploration of how specific conditions might lead to observable consequences in different universes. Additionally, researchers use cosmological and astrophysical observations to help validate aspects of the multiverse hypothesis. For example, anomalies observed in the cosmic microwave background radiation or the large-scale structure of our universe may offer indirect evidence of interactions or influences from other universes. Scientists analyze current observational data to test the predictions made by various multiverse models, seeking patterns that might suggest the underlying framework of a broader multiverse landscape. Furthermore, numerical simulations play a crucial role in studying the multiverse landscape. By creating computational models that simulate cosmic evolution under various sets of parameters, researchers can explore how different configurations might manifest in terms of structure formation, galaxy distributions, or even the fundamental behaviors of particles. These simulations provide valuable insights, allowing scientists to compare predicted outcomes with observational data from our universe. Lastly, discussions around the implications of fine-tuning and the anthropic principle are important in the context of the multiverse landscape. The anthropic principle suggests that the observed values of the physical constants in our universe are not random, but are compatible with the existence of observers like us. This perspective can guide researchers in characterizing the multiverse landscape, as it opens discussions about why certain conditions are favored for life in some universes, while others remain inhospitable. Overall, the concept of a multiverse landscape serves as a fertile ground for research and exploration into the fundamental nature of reality, pushing the limits of theoretical physics and guiding inquiries into the complexities that lie beyond our universe. As scientific methods and technologies advance, the study of the multiverse landscape may reveal deeper connections among the varied realities that populate this theoretical framework, enriching our understanding of the cosmos and our place within it. Future space-based telescopes and observatories hold immense potential for expanding our understanding of the universe's boundaries in several significant ways. By positioning advanced instruments outside Earth's atmosphere, scientists can overcome many limitations imposed by atmospheric distortion and light pollution, allowing for clearer and more detailed observations of distant cosmic phenomena. These telescopes can operate across a wider range of wavelengths, enhancing our ability to probe the universe's intricate structure and beyond. One key area where space-based observatories could improve our understanding is in the study of distant galaxies and the large-scale structure of the universe. Observatories equipped to capture infrared, ultraviolet, and even sub-millimeter wavelengths will enable astronomers to detect light from the earliest stars and galaxies that formed after the Big Bang. By examining these distant celestial bodies, researchers can trace the evolution of the universe, better understand its expansion history, and investigate the formation of cosmic structures that lie at the edge of our observable universe. Additionally, advanced telescopes will enhance the study of dark matter and dark energy, two enigmatic components that influence cosmic dynamics. Instruments designed to map gravitational effects from dark matter and measure the expansion rate of the universe can provide crucial insights into these phenomena. By characterizing these elements, scientists could refine our models of cosmic growth and ultimately extend our understanding of structures and influences located beyond our observable limits. Moreover, future space-based observatories will enhance our ability to detect gravitational waves, particularly through missions designed for gravitational wave astronomy. Observatories like those inspired by the laser interferometer space antenna concept could measure gravitational waves from merging black holes and neutron stars on a cosmic scale. This capability will allow for insights into high-energy events occurring far beyond our galaxy, potentially connecting us with phenomena that shape regions of space well outside our observable universe. Finally, beyond merely observing the known universe, space-based telescopes may also facilitate the study of the cosmic microwave background radiation in greater detail. Increased precision in mapping temperature fluctuations can provide information on the early universe's conditions and potentially reveal facets of cosmic inflation or anomalies that hint at structures lying beyond the observable limits. As these technologies and missions are developed, they will empower researchers to not only gaze deeper into the cosmos, but also to confront the fundamental questions of existence concerning the universe's boundaries and its larger structure. The insights gained could reshape our understanding of the universe and lead to new theories about the nature of reality, further illuminating the intricate connections that may exist between our universe and others beyond our current observational reach. Artificial intelligence is poised to play a transformative role in developing and testing theories about what lies beyond our universe, particularly by enhancing data analysis, simulations, and theoretical modeling. As the volume of astronomical data continues to grow exponentially, AI techniques can assist researchers in efficiently processing vast datasets, identifying patterns, and deriving insights that may not be easily detectable through conventional methods. One major application of artificial intelligence lies in the analysis of data from telescopes and observatories. Machine learning algorithms can be trained to detect subtle signals or anomalies within noise, helping astronomers distinguish between genuine astrophysical events and spurious data. For example, AI could analyze cosmic microwave background radiation to identify irregularities or anomalies that might suggest influences from realms beyond our observable universe, guiding further investigations into the multiverse or other cosmic phenomena. AI can also enhance the modeling of complex physical systems and the simulations used to explore theoretical predictions. In the realms of cosmology and particle physics, researchers often rely on computational models to simulate the behavior of matter and energy under various conditions. AI techniques can optimize these simulations, allowing scientists to explore a broader range of scenarios and factors, potentially revealing new aspects of how different types of matter and dark energy interact. This predictive power can inform tests of existing theories while generating new hypotheses regarding what might exist beyond the observable cosmos. Additionally, artificial intelligence can assist in refining theoretical frameworks by rapidly assessing the viability of competing models. For instance, AI can evaluate how well different theories account for observed phenomena or generate predictions that can later be compared to real-world data. This can streamline the scientific process, enabling researchers to focus on the most promising theories regarding the universe's larger structure or connections to alternate realities. Furthermore, AI's capabilities in natural language processing can facilitate collaboration among researchers by synthesizing vast amounts of scientific literature. By identifying relevant studies, uncovering relationships between findings, and summarizing research, AI can help foster interdisciplinary dialogue that is essential for addressing the complex questions surrounding what lies beyond our universe. Overall, the integration of artificial intelligence into astrophysics and cosmology holds the promise of significantly advancing our understanding of the universe and its underlying structures. As AI tools continue to develop and mature, they will likely provide valuable resources that deepen our exploration of the cosmos, leading to breakthroughs in how we perceive reality and the possible connections we might uncover beyond our observable universe. Advancements in particle physics, particularly those achieved at facilities like the Large Hadron Collider, have the potential to significantly enhance our understanding of multiple universes by probing fundamental questions about the nature of matter, energy, and the forces that govern the cosmos. As researchers conduct high-energy collisions at the Large Hadron Collider, they explore the behavior of subatomic particles under conditions that mimic those present shortly after the Big Bang. This experimental approach not only provides insights into the fundamental building blocks of our universe, but also delves into theories that suggest the existence of multiple universes. One potential contribution of the Large Hadron Collider to the multiverse concept lies in the search for new particles and interactions predicted by extensions of the standard model of particle physics. For instance, certain theories, such as supersymmetry or string theory, imply a richer tapestry of particles than those currently known. Discovering these new particles could provide evidence for the multiple dimensions and energy states associated with multiverse theories. If researchers detect phenomena like extra dimensions or previously unknown particles, it could support the idea that our universe is connected to others in a more intricate multidimensional framework. Additionally, the exploration of the Higgs boson's properties plays a critical role in understanding the early universe's conditions. The discovery of the Higgs boson at the Large Hadron Collider confirmed one of the major predictions of the Standard Model, yet its full implications are still being investigated. The mechanism behind the Higgs field and how it interacts with other particles might shed light on the mechanism of cosmic inflation, an early rapid expansion thought to set the stage for our universe's structure. If inflation can be linked to a broader theory that includes multiple universes, then enhancement in our understanding of the Higgs boson could also open avenues for exploring those connections. Furthermore, high-energy collisions in particle accelerators like the Large Hadron Collider may provide insights into the early universe's dynamic processes, including phase transitions that could give rise to other universes. Theoretical models suggest that in a multiverse scenario, different regions could experience varying vacuum states, leading to distinct universes with their own physical laws. Investigating how particles behave during extreme conditions might unveil clues about the processes leading to such cosmic bifurcations. Lastly, advancements in particle physics resulting from experiments at the Large Hadron Collider can also enhance our understanding of dark matter and dark energy, the mysterious components that dominate the universe's mass-energy budget. As researchers explore the interactions and properties of these elusive entities, the implications may point toward connections to other universes, suggesting how different configurations of dark matter may manifest in separate realms. In conclusion, the work conducted at particle physics facilities like the Large Hadron Collider is invaluable in expanding our knowledge of fundamental principles governing the universe. As scientists continue to decipher the intricacies of particle interactions, they pave the way for a deeper understanding of the multiverse, potentially revealing connections to alternate realities and reshaping our comprehension of the cosmos as a whole. The idea of our universe being a cosmic cell within a larger living superentity is a thought-provoking concept that invites philosophical and scientific contemplation regarding the nature of existence and reality. This notion implies that not only is our universe part of a grander structure, but it also possesses characteristics similar to biological systems, suggesting a form of interconnectedness and hierarchy in the cosmos. Imagining our universe as a cosmic cell raises intriguing questions about the nature of life and consciousness at a universal scale. If we consider that just as cells are the building blocks of life, perhaps our universe serves as a fundamental unit of a more extensive, sentient existence. This perspective encourages exploration into how the laws of physics and the principles governing the universe might reflect a comprehensive, underlying order or purpose. Such a view could potentially merge concepts from both cosmology and philosophy, inviting dialogue around the implications of purposefulness in the cosmos. Furthermore, this idea could lead to the exploration of how interactions occur between different cosmic cells. Just as biological cells communicate through chemical signals or electrical impulses, different universes might interact or influence one another in ways that we have yet to understand. Theories in physics, including those addressing quantum entanglement or parallel universes, could inform this exploration, suggesting that connections between our universe and others could exist within a metadimensional framework. The concept of our universe as part of a living super-entity could also reflect on the structures that govern universes, akin to how biological systems maintain homeostasis and respond to environmental changes. The properties of dark matter, dark energy, and the observed acceleration of our universe's expansion could signify an awareness or adaptation mechanism, hinting at a dynamic, evolving cosmic system. Ultimately, while the idea of our universe as a cosmic cell within a larger living entity remains speculative, it encourages a multidisciplinary approach to the questions surrounding our existence. It invites scientists and philosophers alike to ponder the larger implications of the universe's intricate tapestry and our place within it, propelling us toward richer discussions on consciousness, interconnectedness, and the nature of existence itself. As our understanding of the cosmos evolves, such imaginative concepts could enhance our quest for knowledge, inspiring us to investigate and explore the profound mysteries of life and the universe. The concept of cosmic DNA, encoding the properties of different universes within a multiverse, presents a fascinating metaphor for understanding the underlying frameworks that may govern various realities. Just as DNA carries the genetic instructions that determine the characteristics and functioning of living organisms, this idea suggests that there could be fundamental principles or codes that dictate the properties and laws of different universes. In terms of physical theories, cosmic DNA might represent a set of variables or constants that define the distinct characteristics of each universe in a multiverse scenario. These variables could include fundamental forces, particle masses, the strength of gravity, and the nature of dark matter and dark energy. By elaborating on the underlying rules and initial conditions, cosmic DNA could provide a systematic way of describing how universes branch off or differ from one another. One way to approach the idea of cosmic DNA is through the lens of string theory and its multitude of solutions. In this framework, there is a wide variety of ways to compactify extra dimensions, each leading to its own configuration of physical laws and constants. In this sense, the different compactification schemes could be thought of as distinct genomes, with each scheme encoding a unique universe's behavior. Consequently, the properties observed in our universe, such as the values of physical constants, could be determined by the particular structure of this cosmic DNA. Another consideration lies in the potential role of quantum mechanics in shaping the cosmic DNA concept. Certain interpretations of quantum mechanics suggest that every quantum event creates branches of reality, leading to divergent outcomes across multiple universes. The rules governing these events and their interactions could form another layer of this cosmic DNA, where the nature of quantum phenomena dictates the evolution and properties of each universe in the multiverse. Furthermore, the idea of cosmic DNA invites contemplation of how interactions might occur between different universes. If each universe encodes its own set of physical laws and unique traits, could there be pathways or connections facilitated by shared structures? This speculation echoes notions found in theories related to wormholes or higher dimensional pathways that connect universes, suggesting a more intricate web of relationships across the multiverse. Ultimately, the concept of cosmic DNA serves as a compelling metaphor for exploring the fundamental principles that may define the nature of reality across multiple universes. As researchers continue to probe the boundaries of theoretical physics and cosmology, this idea encourages deeper reflection on how the rules of existence might manifest in diverse ways, shedding light on the complex tapestry of the cosmos and inviting further inquiry into the very fabric of reality itself. The notion of the expansion and contraction of universes as part of a cosmic respiration cycle presents a captivating idea that likens the cosmos to a living, breathing entity. This concept suggests that universes undergo a rhythmic sequence of expansion and contraction, akin to the inhalation and exhalation processes in biological organisms. Such a model could provide a compelling framework for understanding the dynamics of our universe and the potential existence of others. In a cosmic respiration model, the expansion phase could signify a period of energy dispersal and growth, driven by the initial conditions following the Big Bang. During this phase, the universe stretches, galaxies move apart, and cosmic structures evolve. This aligns with our current understanding that the universe has been expanding since its inception, supported by observational evidence such as the redshift of distant galaxies. Conversely, the contraction phase could represent a time when the gravitational forces begin to dominate, pulling matter back together. This stage might lead to a big crunch, where the universe collapses into a singularity, possibly setting the stage for a new cycle. In this way, the universe could transition from an expansionary state back to a collapsed state, resembling the exhalation process that expels air before drawing in fresh breath again. The concept of cosmic respiration raises intriguing questions about time, space, and the nature of existence itself. If multiple universes exist and follow similar cycles, it may imply that the life cycles of distinct universes are interconnected in some way. The rhythmic process may not only apply to our universe but could also influence other realms within a broader multiverse framework, with cycles of expansion and contraction leading to diverse properties and conditions in each universe. Moreover, this model invites inquiry into the roles of dark energy and dark matter in the cosmic respiration cycle. Understanding how these components influence the expansion and contraction dynamics could provide deeper insights into the underlying mechanics of the universe's life cycle. If dark energy continues to drive the accelerated expansion we currently observe, it may be essential in determining whether the universe will eventually contract or enter a new phase altogether. Ultimately, the idea of cosmic respiration serves as a thought-provoking metaphor for the evolution of the universe and the potential existence of other cycles beyond our perception. As scientists explore the implications of this concept and investigate the dynamics of cosmological expansion and contraction, they could uncover pathways to understanding fundamental questions about the nature of reality, the existence of multiple universes, and the profound connections that might unite all forms of existence across the cosmos. The concept of inter-universal synapses proposes a fascinating framework for understanding how communication or energy transfer might occur between different universes within a multiverse. This metaphor suggests that just as biological synapses facilitate communication between neurons, allowing information to flow within a complex nervous system, inter-universal synapses could serve as channels that enable interactions between distinct realities. One potential mechanism for these inter-universal synapses is rooted in the idea of higher dimensions or hidden dimensions that extend beyond the familiar three dimensions of space. Theoretical frameworks such as string theory propose the existence of additional dimensions that could allow for connections between parallel universes. In this context, these synapses might represent pathways or bridges that link higher dimensional structures, enabling matter, information, or energy to traverse between universes. These inter-universal synapses could manifest as gravitational or quantum entanglement links between particles or energy fields residing in different universes. If particle states are entangled across universes, interactions in one universe might influence corresponding states in another universe instantaneously. This could provide a mechanism for information exchange or coordination between systems that, under classical physics, would be completely isolated from one another. Additionally, the notion of interuniversal synapses could involve exotic forms of matter or energy, hypothetical particles that may not exist in our universe but instead reside in others. These particles could facilitate energy transfer across the multiverse, perhaps enabling the sharing of resources or physical properties. This idea invites speculation about new forms of physics and the potential for utilizing these connections to understand the fundamental laws governing each universe. The study of such interuniversal connections could also lead to intriguing discussions about the implications for cosmological principles like conservation of energy and information. If communication and energy transfer were possible between universes, it might modify our understanding of how these laws operate when considering a broader multiverse context. This could inspire fresh insights into foundational questions regarding the nature of existence and the relationship between universes. Ultimately, the concept of interuniversal synapses offers a rich narrative for exploring theoretical connections between universes and prompts a deeper consideration of how the multiverse might function. As scientific research continues to push the boundaries of our understanding, such ideas may inspire new models of reality that expand our grasp of the cosmos and the potential for interactions across its many facets. The idea that dark energy might result from our universe being digested by a larger cosmic organism presents a fascinating and imaginative framework for understanding the dynamics of the cosmos. Dark energy is currently recognized as the mysterious force that drives the accelerated expansion of the universe, accounting for about 70% of the universe's total energy density. This conceptualization suggests that rather than being a mere force or constant, dark energy could be a sign of something more profound and interconnected with a larger living entity. If we were to consider the possibility that our universe is a part of a cosmic organism, it raises intriguing questions about what it means for one universe to engage in such a biological process. In this scenario, the accelerated expansion driven by dark energy might be akin to metabolic processes, where the universe is being transformed or utilized by a larger cosmic structure. This might imply that as our universe expands, it is releasing energy or information into this greater being, effectively becoming part of a broader system that influences not only itself, but other regions or entities as well. This metaphorical digestion could also explore relationships between different parts of the cosmic environment. Just as biological systems maintain homeostasis, a cosmic organism might oversee the balance and interactions between various universes or cosmic structures. The properties of dark energy, as they influence the expansion rate, may indicate a mechanism by which energy circulates or is exchanged with the larger entity, suggesting a dynamic, interdependent relationship rather than an isolated existence. Furthermore, this idea could fundamentally challenge our current understanding of dark energy and the universe's fate. The notion that our universe might be alive in some sense posits that cosmic evolution may involve more than just physical processes, introducing the idea of purpose, intentionality, or even conscious influence in cosmic dynamics. If dark energy is a byproduct of a larger organism's interaction with our universe, it could imply that the universe's expansion is part of a grander strategy for growth, evolution, or maintenance of balance in a cosmic ecosystem. Ultimately, while the notion of our universe being digested by a larger cosmic organism is speculative, it invites rich philosophical and scientific discussions about the nature of existence and the interconnectedness of all things in the cosmos. Such a perspective could inspire new lines of inquiry into what cosmology and biology might share at deeper levels, prompting us to rethink the conventional boundaries that separate life, energy, and the universe itself. As scientists continue to explore the mysteries of dark energy and the structure of the cosmos, they may uncover insights that bridge these imaginative concepts with rigorous scientific investigation, expanding our understanding of the universe and our place within it. The concept of probability waves is closely tied to quantum mechanics, where particles do not have definite positions, but instead exist as probabilities described by wave functions. These probability waves can span across space and time, suggesting the potential for various outcomes and states to coexist until an observation collapses the wave function into a definite result. When considering the edge of our universe, or the boundary of our observable cosmic horizon, the notion of probability waves becomes particularly intriguing in its implications for the formation of new realities or universes. At the edge of our universe, these probability waves could represent the uncertainty inherent in quantum phenomena, allowing for fluctuations that could give rise to new configurations of matter and energy under specific conditions. This idea aligns with theories of cosmic inflation, which suggest that tiny quantum fluctuations in the early universe led to the large-scale structure we now observe. If such probability waves can create diverse regions of space with distinct properties, it raises the possibility that they could initiate processes that generate entirely new realities or pockets of existence. These probability waves might also suggest mechanisms for the emergence of parallel universes as described in many worlds interpretations of quantum mechanics. In this framework, every quantum event produces branching realities in which every potential outcome occurs in its own distinct universe. If the edges of our universe are suffused with probability waves, the interactions and collapses of these waves may lead to the creation of new branches, fostering the existence of alternative realities that develop based on different paths of quantum events. Furthermore, the dynamics of probability waves could influence how components of our universe interact with hypothetical structures or realms beyond our observable limits. For instance, if probability waves extend from our universe to areas that are not directly observable to us, they may establish connections that facilitate the exchange of energy, information, or even matter with other realities. Such interactions could play a role in the evolution of these new realities, perhaps allowing them to draw on the foundational properties of our universe while also developing unique characteristics of their own. As researchers continue to explore the foundational aspects of quantum mechanics and cosmology, the study of probability waves at the edges of our universe could yield insights into the complex relationships between different realities. This exploration not only challenges our understanding of the nature of reality, but also invites contemplation about the interconnectedness of all existence, potentially expanding our view of the universe and the myriad possibilities that may spring from its inherent uncertainties. The idea that our universe could be a cosmic hologram projected from a higher dimensional reality is a fascinating hypothesis that merges concepts from quantum mechanics, theoretical physics, and cosmology. This notion is grounded in the holographic principle, which posits that all the information contained within a volume of space can be represented as a two-dimensional surface, suggesting that the three-dimensional experiences we perceive might arise from information encoded on a lower dimensional boundary. If our universe is indeed a hologram, it would imply that the fabric of reality as we know it is fundamentally different from our intuitive understanding. In this framework, the extensive three-dimensional universe we experience could be a projection of information residing in higher dimensions. This could mean that the underlying reality is more complex and interconnected than we currently comprehend, with higher dimensions providing the scaffolding for the physical phenomena observed in our universe. Exploring the concept of a cosmic hologram raises enticing questions about the nature of existence and the relationship between reality and perception. If our universe is a projection, it suggests that the perceived laws of physics and the constants we recognize may simply be reflections of deeper underlying principles. This could lead to a re-evaluation of fundamental concepts such as time, space, and even causality, as they might be emergent properties rather than fundamental aspects of existence. Moreover, if this holographic projection originates from a higher dimensional reality, it implies that there could be additional dimensions influencing the behavior and interactions of particles and forces within our universe. This could provide a framework for exploring connections between different scales of reality, possibly linking the quantum realm with cosmic structures. The nature of dark matter and dark energy could also be reconsidered in this context, as they may be manifestations of higher dimensional effects, rather than independent entities. The synchronicity of information encoding in a holographic universe could also have profound implications for our understanding of black holes and entropy. Physicists Jacob Bekenstein and Stephen Hawking's work on black hole thermodynamics suggests that the information content of a black hole is proportional to its surface area, aligning with the holographic principle. This invites deeper inquiries into how information, energy, and the fundamental nature of black holes intersect with the broader cosmos if our universe is indeed a holographic projection. In conclusion, contemplating the idea of our universe as a cosmic hologram projected from a higher dimensional reality challenges us to rethink deep-rooted assumptions about existence and reality. As researchers continue to investigate the implications of the holographic principle and its relationship to fundamental physics, this perspective may lead to groundbreaking insights, expanding our understanding of the universe and possibly unveiling a more intricate tapestry of reality than we currently perceive. The concept of quantum foam wormholes arises from the intersection of quantum mechanics and general relativity, suggesting that at the smallest scales, specifically at the Planck scale, space-time is not smooth and continuous but instead exhibits a foamy, fluctuating structure. This idea posits that the fabric of the universe is made up of tiny, constantly changing bubbles or foams that could create transient connections or tunnels between different points in space-time, potentially linking our universe to others in the multiverse. At the heart of this concept is the notion of wormholes, which are theoretical passages through space-time that could connect distant regions or even different universes. Quantum foam proposes that these wormholes might exist in a fluctuating state at incredibly small scales, effectively connecting points in both our universe and possibly other parallel universes. Rather than being stable structures, these wormholes might pop in and out of existence, appearing momentarily as quantum fluctuations occur. These transient connections could facilitate a form of communication or interaction between universes, allowing for the exchange of information, particles, or energy across the boundaries of different realities. Such interactions might not be observable in the traditional sense, as the wormholes would only exist for a fleeting moment, emphasizing the fundamentally probabilistic nature of quantum mechanics. Moreover, the chaotic nature of quantum foam could mean that while the connections are ephemeral, they could have significant effects on the dynamics of the involved universes during their brief existence. The implications of quantum foam wormholes extend into the realm of information theory and the study of holographic principles. If information is fundamentally linked to the structure of space-time, as the holographic principle suggests, then these tiny connections could hold keys to understanding how information and energy are transferred across cosmic scales. Researchers have theorized that exploring these connections might help illuminate the behaviors of dark matter and dark energy, both of which remain enigmatic components of our universe. Additionally, the existence of these wormholes could offer alternative explanations for certain quantum phenomena, bridging the gap between the macroscopic and microscopic worlds. They would suggest that the behavior of particles is not entirely limited to our familiar three-dimensional space, but could entail complex interactions with higher dimensional structures or neighboring universes. In conclusion, the idea of quantum foam wormholes connecting our universe to others at the smallest scales presents an exciting frontier in theoretical physics. As researchers delve deeper into quantum mechanics, general relativity, and the nature of space-time, the exploration of these wormholes may reveal profound insights into the interconnectedness of the universe, helping to unlock the mysteries of existence and the potential for interactions among diverse realities. The idea that the constants of nature in our universe might be determined by a cosmic evolutionary algorithm presents a captivating model for understanding the inherent features of our universe and their origins. This concept suggests that instead of being fixed or arbitrary, the fundamental constants, such as the gravitational constant, the speed of light, and the fine structure constant, could emerge through a dynamic process akin to natural selection or optimization in biological evolution. In this framework, The cosmic evolutionary algorithm would act as a guiding mechanism that iteratively explores various configurations of these constants across a vast landscape of potential physical realities. Much like how genetic variations can be assessed through survival and reproduction in biological organisms, different settings of the physical constants could lead to varied outcomes for the universe's structure and the emergence of life. Those configurations that promote stability, complexity, or the conditions favorable for the development of structures like galaxies, stars, and eventually life could be selected to characterize our universe. Such an algorithm could operate across a multiverse, where countless universes exist with different combinations of physical constants. Within this multiverse scenario, some universes may undergo various evolutionary processes driven by the interplay of their constants, with certain combinations proving more conducive to complexity and stability. Over time, this evolutionary filtering could enhance the likelihood of universes that possess the balance of forces and structures needed to allow for the emergence of life and consciousness. The implications of a cosmic evolutionary algorithm extend not only to the constants of nature, but also to the fundamental laws of physics. If these laws are adjustable or can fluctuate within this algorithmic framework, it suggests that our universe could be the product of an ongoing dynamic process rather than a fixed endpoint. This could lead to richer explorations of how laws governing quantum mechanics, gravity, and other fundamental interactions might interact to produce a complex universe capable of evolving through time. Furthermore, this perspective challenges our understanding of fine-tuning, the apparent precision with which the constants of nature allow for life and complexity. If the constants are outcomes of a cosmic evolutionary process, it raises profound questions about the nature of life itself and its relationship with the cosmos. Life, in this view, becomes an essential factor in the evolutionary algorithm, potentially influencing how the constants are set or modified in neighboring universes. Ultimately, the concept of a cosmic evolutionary algorithm provides a compelling avenue for exploration in cosmology, physics, and philosophy. As researchers continue to investigate the foundations of the universe and the nature of physical constants, this idea invites deeper reflection on the interconnectedness of existence, evolution, and the mysteries of the cosmos, paving the way for new insights into our understanding of reality. The concept of reality fractals proposes a fascinating framework in which the structure of the universe exhibits self-similar patterns across different scales, leading to the idea of infinite nested universes. Fractals are mathematical constructs that display repeating patterns at various levels of magnification, such that smaller sections of the fractal resemble the whole. Applying this concept to cosmology suggests that the universe might not only have similarities in structure at large scales, such as galaxies clustering in filaments, but also duplicate configurations at smaller and smaller scales, potentially leading to the existence of nested universes within a larger cosmic structure. In this model, every universe could be viewed as a fractal, with its own set of physical laws and properties, shaped by similar underlying principles. Large-scale structures, such as galaxy clusters, could maintain features indicative of the same principles governing phenomena at smaller scales, like atomic structures or subatomic particles. This notion implies that as one zooms closer to any point in the universe, they might discover structures that replicate the larger cosmic framework, suggesting a uniformity of patterns dictated by fundamental laws of physics. The concept of reality fractals might also furnish an explanation for the multiverse hypothesized in modern theoretical physics. If our universe is just one iteration of a fractal pattern, then there could be countless other universes that emerge from the same underlying principles but manifest distinct characteristics. Each nested universe would retain certain features of the larger fractal pattern, while diverging in essential ways due to variations in initial conditions, physical constants, or dimensional constraints. Moreover, the idea of nested universes presents intriguing implications for our understanding of quantum mechanics and the behavior of particles. Quantum phenomena might also exhibit fractal-like behavior, suggesting that particles interact with each other and with their environment through self-similar mechanisms that operate across scales. This could lead to the idea that the fundamental processes governing particle behavior are inherently tied to the larger cosmic structure. The notion of reality fractals might also challenge our perceptions of time and sequence within the cosmos. If the structure of reality operates on fractal principles, it could imply that different layers of existence experience time differently or even influence one another. The interconnectedness of these layers might allow for unique interactions that span universes, further enriching the complexity of reality. Ultimately, the idea of reality fractals creating infinite nested universes provides a compelling lens through which to explore the interconnectedness of structures across various scales. As scientists continue to investigate the nature of the cosmos, this concept could lead to innovative theories and models that encourage deeper inquiry into the fundamental principles governing existence. Such inquiries might reveal not only the nature of our universe, but also the nature of reality itself, reshaping our understanding of the cosmos as a whole.